Okay, so we're going to start our revision with Unit 1. The first topic of Unit 1 is, of course, movement and position. We know that acceleration is the rate of change of velocity. Its equation A is equal to V minus U over T. Acceleration is caused by the resultant force. Now, velocity is the rate of change of displacement, and displacement is the net distance traveled in a single direction. And of course, we measure it using a straight line. So to understand the difference between distance and displacement, this diagram is really helpful. Next up, we have speed. Now, speed is basically velocity, but without the direction. So we take the overall distance traveled for the entire journey and divide it by the time taken. In symbols, we say V is equal to S over T. Now, this leads us to the difference between vector and scalar quantities. Vector quantities have both magnitude and direction, for example, velocity, whereas scalar quantities such as speed have the magnitude only. You need to know the examples of vector and scalars, which you will learn in other units and topics as well. Okay, next up, we have the idea of acceleration. Now, as we said previously, acceleration is the rate of change of velocity. For velocity to change, the speed at which the object is moving doesn't have to change. So in instances like this, where the particle is curving up like this, is the particle accelerating? Yes, the particle is accelerating. Why? Because the velocity changes. Now, why does the velocity change? The velocity changes because the direction is changing. The speed, however, can be constant and we can still be accelerating. This is going to become useful when we look at the effects of fields on charged particles in Unit 6 and 7. And of course, we need to know that the higher the resultant force, the direction is going to change faster. We will look at this in more detail when we look at Newton's second law, F is equal to ma. Then we have graphs. Distance time graph, the gradient of it gives the speed. The gradient of the speed or velocity time graph gives you the acceleration. And the area under the speed or velocity time graph gives you the distance traveled. So if the question says that the curve of the speed velocity time graph is upwards, then we know that the gradient is increasing. And because the gradient is increasing, we know that the speed is increasing. And because we know that the speed is increasing, it's going to be accelerating. And by the way, I meant distance time graph. So in a distance time graph, if the curve is upward, the gradient is speed, the speed is increasing. Speed is increasing means it is accelerating. We then have to look at the measurement of the average speed of a moving object. It's actually very easy. Just think about the equation V is equal to S over T. How do we measure the distance? We measure the distance using the meter ruler. How do we measure the time taken? We measure it using a stopwatch. And of course, to be reliable, to get reliable results, we repeat the whole experiment, find the mean, and then we do our calculation using the space of distance over time. Or to be better, for better results, we can plot a distance time graph. So different distances, different times, we plot that and we find the gradient using the best fit line. We then have to look at the equation of uniformly accelerated motion, v squared to u squared plus 2as. This is going to be used in questions where you don't have the time taken. So you have the distance information, acceleration information. You can find the initial or final velocities. These kind of questions are quite easy. And of course, the standard value that we have to use in international GCSE, g is equal to 10 meters per second square. This is the acceleration of an object in free fall without drag, without air resistance. Moving to topic 2, we have forces and shape. Of course, we have to know Hooke's law. Hooke's law states that the spring force is directly proportional to the extension. In terms of direction, the spring force is going to be opposite to the direction of the extension. So if the spring is going to get longer, which means that the extension is downwards, the spring force is going to be upwards. If the spring is going to get compressed, which means the extension is upwards, the spring force is going to be downwards. Now, you don't need to know the equation F is equal to minus kx for international GCSE questions, but there has been one question in the past where you talk about the force and extension direction, so this is useful to know. And we can investigate and look at Hooke's law on a graph. So if we look at a force extension graph, the portion of the graph which has a straight line is representing Hooke's law, and that is because it is a straight line and it passes through the origin, so force and extension are directly proportional. And of course, that's what directly proportional means. Directly proportional, graphically speaking, means that the line is straight and it passes through the origin. You'll have some questions regarding direct proportionality for other topics as well. So this is useful to know. And of course, if you keep increasing the extension, you will reach the limit of proportionality. This is the extension beyond which the force is no longer proportional to the extension. So Hooke's law can no longer be applied. But you still can experience elastic behavior. You only lose elastic behavior once you reach the elastic limit, which is the extension after which, even when the applied force is removed, the spring no longer returns to its original length. So if you have to draw a line, you're going to have to draw a line such that it is going to be above extension 0. And that is because it loses its elastic behavior. Now, what is elastic behavior? Elastic behavior means that the spring will return to its original length of shape even after the stretching force is removed. But if you lose the elastic behavior by reaching beyond the elastic limit, the spring will no longer return to the original length. Which is why if you have to draw the line, it is always going to be above zero because the spring will always be a little longer than the original, than the initial starting length. And of course, this classic investigation is very common. It's a very common question, but it's also very easy. So what do? You start with measuring the original length using a ruler. And of course, using a set square is going to help improve the accuracy of your measurements. And then you add the masses to cause the extension. And once you add the mass, you measure the stretch length. To find the extension, you basically find the difference between the stretch and the original length. And you repeat this by adding different masses and keep extending the spring. And of course, to get reliable results, what do? You repeat more than once for each mass and you calculate the mean extension. That's pretty much it for chapter 2. We then move on to chapter 3, which is forces and motion. We look at the effect of resultant force on motion. If the resultant force is zero and the object was remaining at rest, it will continue to stay at rest. If the object was already moving, it will keep moving at that same constant velocity. This is called Newton's first law, but you do not need to know this law by name. You just need to understand the concept that if the resultant force is zero, it will keep staying at rest, or it will keep moving at the constant velocity. If the resultant force, however, is non-zero, then the object is going to accelerate, and it is going to accelerate in the direction of the resultant force. This means that if the object is moving to the right, but the resultant force is to the left, it is going to cause deceleration, which means that the velocity is going to decrease. This is called Newton's second law, and it also states that the resultant force is directly proportional to the acceleration, meaning the greater the resultant force, the greater the acceleration. And this gives us the equation F is equal to ma, which we need to use for calculations as well. This leads us to the concept of stopping distance. Now, stopping distance is the sum of the thinking distance and the braking distance. The thinking distance is both the thinking distance and the braking distance. They are both affected by the speed of the car. The thinking distance, however, is affected by the driver's condition, and that is because it affects the driver's reaction time, which means that there is more time taken between the moment the driver sees the threat on the road and the moment he steps on the brakes. The braking distance, however, is affected by environmental conditions such as the road surface, as well as the condition of the car, such as the condition of the tire surface, the condition of the brakes, how old the brakes are, and how heavy the car is, or the mass of the car. And that is because these factors are going to affect the braking force, and that is going to affect the deceleration, which is in turn going to affect how long it takes for the car to stop, which is in turn going to affect how much the car travels while it is braking. Then we have the concept of terminal velocity. This is actually very common, and we can see this in a variety of places: objects falling from the sky, objects falling through water, and etc., etc. So it starts with an object with weight. Now the weight is going to be what's causing it to accelerate downwards. So weight is going to be the resultant force. It's going to accelerate downwards. But as it accelerates, we are going to gain something called drag or air resistance. As the speed increases, the drag force is going to increase. And because the drag force upwards is going to increase, the resultant force, the difference between the weight and the drag, is going to get smaller and smaller, which causes the acceleration to decrease. Eventually, the drag force and the weight force are going to become equal, making the resultant force equal to zero, and therefore the acceleration is also going to become zero. In some cases, we will have a parachute. Now, when we open the parachute, what happens is the surface area that is in contact with the air is going to increase, and that is going to dramatically increase the drag force or the air resistance. And therefore, the drag force is going to become greater than the weight force, the downward weight force, which is going to cause the resultant force to become upwards. However, because the object is still moving downwards, right? The motion is downwards, but the acceleration is upwards. That is going to cause something called deceleration, which means that the velocity or the speed is going to decrease. Because the speed decreases, the drag force is going to decrease. Remember, the drag force or the air resistance is going to increase in proportional to the speed. So because the speed is going to decrease, the drag force is going to decrease. So eventually the drag force will become equal to weight again, and that is going to cause the second terminal velocity because there is no resultant force. Here you can see how we write the explanation for that as well. All right, and that is going to be it for the third topic of Unit 1. Let's now move on to the fourth topic, momentum. Now remember guys, momentum is a paper 2 question, so double science students will not need to know momentum. So what is momentum? Well, momentum is a measure of how difficult it is to stop a moving object or how difficult it is to change the direction of it. You do not need to know the definition of momentum, you just need to have an intuitive understanding of what momentum is. You do, however, need to know the equation P is equal to mv, and that momentum is the product of the mass and velocity of the object, which gives us the units kilogram meter per second. And of course, momentum is a vector, so you need to be very, very careful of the direction. Conservation of momentum questions are very, very common. The key concept is that the total momentum before collision is equal to the total momentum after the collision. So when you're doing the calculations, you need to be taking care of the direction. So if the object was moving to right initially, but then it moves to the left, what you have to do is you have to negate the value of the velocity when the object moves to the left. Then we have the rate of momentum questions. Now the formula is that F is equal to mv minus mu over t. It comes from F is equal to ma. Now A is equal to v minus u over t. So we just chuck m in front and we just multiply inside. Okay. The question that we're going to get is, of course, the calculation question with the formula. And we're also going to get questions regarding how the force during impact on a collision is going to be reduced. So those kind of questions are very, very easy. All you have to do is think about the formula in your mind and go for one component at a time. So we're starting with the denominator, which is time taken. Now, when we have a soft object in between the collisions, such as a cushion, the time taken during the impact or the deceleration time is going to increase. However, the change in momentum is the same because the initial and the final velocity are going to be the same. The mass is going to be the same. So the numerator is going to be the same. But because the denominator time taken has increased, the overall fraction is going to decrease. That overall fraction we refer to as the rate of change of momentum. So the rate of change of momentum decreases. Because the right-hand side is going to decrease, the left side, the force must also decrease. And those 3 points right there are going to give you 3 marks for those explanation questions. Last but not least, we have Newton's third law of motion. Newton's third law of motion is also a paper 2 topic, and this is the only law that you need to know by name and that you need to be able to apply in the questions. Very simple, you just need to know this line. For every force, there is an equal and opposite reaction, which is why the force of B on A is equal to the force of A on B in terms of magnitude, but they are opposite in direction, which is why we have a negative sign right there. Final topic of Unit 1 is going to be moments. This one is also a paper 2 topic. Now, what is the moment of a force? The moment of a force is the turning effect of a force. So if you have an object that is attached to a pivot and you apply a force to it, you are going to measure how much it turns. So the measure of how much it turns is the moment. Moment is the product of the force and the perpendicular distance from the pivot. Because we're taking the perpendicular distance from the pivot, you want to make sure that the distance measurement and the force arrow are perpendicular. Of course, we have principle of moments, which is that the sum of clockwise moments is equal to the sum of anti-clockwise moments. And we have to be very careful with the clockwise direction and anti-clockwise direction, and we have to make sure that the distances are all perpendicular. And of course, we have the difficult explanation questions, which I break down in detail in my video on moments explanation focus, so you should definitely check that out. But yeah, that's pretty much it for Unit 1 topic. I hope you guys have a blast with revising this one for the exam. Thank you. So we're now going to take a look at Unit 2 electricity. Under Unit 2, we have a variety of different topics, starting with mains electricity, where we're going to be looking at the effect of safety devices. We'll then take a look at current and voltage in series and parallel circuits, and we'll move on to investigating electrical resistance, particularly Ohm's law. We'll also have to look at IV graphs and how we obtain those graphs in a practical where we investigate the relationship between current and voltage for different types of components. We'll end with investigating static electricity, such as the use of static electricity as well as its dangers. So before we dive into mains electricity, we need to know what current, voltage, power, and energy are, and the formula and equations relating those values. Now, starting with current, guys. Current is basically the rate of flow of charge. You can find it by dividing the amount of charge transferred divided by the time over which that charge is transferred. The unit, of course, is amperes, and it is a scalar quantity. Voltage is going to be the electrical energy transferred per unit charge. So you divide the energy transferred by the amount of charge that carries it. It's also a scalar quantity, and the unit is in volts. Now, more often than not, the equations for these will be given as Q is equal to IT and E is equal to QV because they are more useful. However, by rearranging them, we can have an intuitive feel and understanding for what current and voltage are. Here is an example question from 2024 May and an example mark scheme that asks you to define the term voltage. Next up, we have power. Power, guys, remember, is the rate of transfer of energy. We'll learn this in Unit 4. And the way we derive this equation is by using voltage and current. Now, we know that voltage is the rate of transfer of energy per unit charge, and current is the rate of transfer of charge. So if you multiply E over Q, voltage, with Q over T, current, what you get is Q cancels out and you get E over T. Now E over T, rate of transfer of energy, or the rate at which work is done, is power. And therefore you can get power of a component by multiplying the voltage and the current. So that's going to give you the value of how much energy an electrical appliance is taking in every single second. Now, if you want energy, you basically just multiply IV with T, and that's because power is a rate of transfer energy. So if you want energy, you just multiply power with time. So power is IV, so you just get IVT. These equations are going to be very important when you do your calculation questions. All right, now let's take a look at the components of a plug. This is really important. Now, in a plug, you need to know that there are three types of wires. We have the earth wire, the neutral wire, and the live wire. And you need to know what each wire does. The live wire is the wire that's going to be carrying the electrical energy from the power station to your appliance. So it's going to be the one carrying your current. The neutral wire is to complete the circuit. Remember, guys, current only flows when the circuit is complete. So the neutral wire, what it does is it returns the current back to the power station so that it forms a complete circuit, a complete loop, allowing electricity to flow. The earth wire is connected to the metal casing of an appliance. Now, some appliances do not have an earth wire, but the main function is that the earth wire is going to prevent electrocution by taking the electricity away from the user into the ground. We also have a fuse, and the fuse is connected to the live wire. The role of the fuse is to prevent overheating by cutting off the current early to prevent the formation of electric fires. Now, the thing that we need to know is that the fuse is always connected to a live wire, and that's because the live wire is what's going to take current to the appliance in the first place. We cannot put the fuse in the neutral wire because even if the fuse cuts off the neutral wire, current can still come to the user through the live wire. So here is an example question. This is not 4PH1, this is actually from 4PH0. But once you're done with your 4PH1 past papers, you can try these 4PH0 questions out because the concepts are the same. So here is another question from 4PH0. Okay, now this is going to be a big question that you will often encounter in electricity, and it is going to be a question about how the earth wire and the fuse work together. Now, just to quickly remind you, the earth wire, its role is to prevent electrocution. So you do not want to give the user an electric shock. The fuse function is to prevent overheating by cutting off the current as soon as it starts to overheat due to excessive current. So how are they going to work together? Let's take a look. Now we are going to be looking at an appliance with a metal casing. Remember, guys, metal is a conductor. So if you touch the casing, it's going to conduct. It's going to conduct in a scenario where the live wire is faulty or broken and the live wire is somehow touching the metal casing, and therefore it is going to make the metal casing live. So once the metal casing is live, if you touch it, you are going to get electrocuted because electricity is going to flow from the live wire to your body. But to prevent that, we have an earth wire. The earth wire has a very low electrical resistance. So what it's going to do is that it's going to make the current flow from the casing to the earth instead of you. So the resistance of the earth wire is much, much lower than the human body. So what it's going to do is that the current is going to flow into the earth and not the person, and therefore it prevents electrocution. It also has another function, and that is because the electrical resistance of the earth wire is so low, what the earth wire can do is that the earth wire can cause a surge in the current. Now, because the current through the earth wire is much higher, the current through the live wire is also going to be much higher. Now, what is this going to do? This is going to cause the fuse to melt because as the current increases, the heating effect causes the fuse temperature to increase, and it's going to melt the thin wire inside the fuse. Now, once the fuse melts, what happens is the current is going to stop, because in the fuse there is a thin wire. If the wire is broken, it's no longer going to be able to transmit the current through the live wire. So what happens is that because the current stops early, it's going to prevent overheating of other wires, and that is going to prevent an electric fire. Now, if we only have an earth wire but no fuse, what's going to happen is that the current is going to exceed normal levels, and therefore it's going to cause an excessively high current. Now, a high current will cause a high heating effect, and the high heating effect will cause the wires to overheat, leading to fires, which is not a good option. So that is a summary of how the earth wire and the fuse work together. Remember, earth wire, electrocution; fuse, prevent fire. Next up, we have to look at circuit breakers and fuses. This is now a very common question that we recently see in recent past papers. So they're going to ask you what the advantage of a circuit breaker is over a fuse. Remember, guys, the circuit breakers can be reset, so they can be reused multiple times, whereas a fuse, once it has been blown, you need to completely replace it with an entirely new fuse. And the other thing is circuit breakers cut off the current much more quicker. They are more, they have a faster response time, and therefore they are going to cut off the current much more quickly. Whereas fuses, you need to wait until the temperature is hot enough so that the thin wire melts. Also, the circuit breakers are more sensitive to changes in current. So even if it's only like 0.5 amperes higher than the normal current, it's going to instantly switch it off. Okay, so this marking scheme, again, is from 4PH0, but it's good for preparing for your 4PH1 questions. Next up, let's take a look at the heating effect of current. Now, the heating effect of current is pretty much a problem, but it is also useful. It is a problem, as we previously discussed, in wires where there is overheating, where there is too much current that can lead to overheating and that can lead to fires. But it is also useful in equipment such as a hairdryer, because you want the wires in the hairdryer to get hot so that the air that you blow is getting hot. It's also useful in things like toasters so that you can toast your bread. So how does the current cause a heating effect? That is what we need to know for our exams. Now, we need to talk about resistance. Now, resistance is a measure of how easy it is, or how difficult it is for the electrons to move. So the higher the resistance, the more difficult it is for electrons to move through a wire and conduct electricity. So because there is resistance, now when it comes to resistance is basically just a matter of collisions between the electrons in the wire and the ions in the giant metal lattice structure. So when the electrons are flowing through the wire, they're going to bump into the ions. So if they bump into the ions more frequently, that means that the resistance is much higher. But if they don't bump into the ions more frequently and they can move more freely, that means that the resistance is much lower, which is why we need to discuss the term resistance when we are talking about the heating effect. Now, resistance means that the electrons in a conductor move and they collide with the ions in the giant metal structure. So when they collide with the ions, the energy is going to be transferred from the electrons, so the kinetic energy of the electrons, to the kinetic store of the ions in the conductor. Now, remember, thermal energy is basically just the sum of the average kinetic energy. So as the kinetic energy of the ions in the conductor increases, the temperature of the conductor itself is going to increase. So that's going to increase the vibration of the ions. Now, as the vibration of the ions increase, the chance of the electrons colliding with the ions increases further, which is going to increase the resistance, and the entire thing is going to repeat, which is why as the wire starts to heat up, it gets easier for the resistance to increase and for the heating effect to become more significant. So basically, all you need to write is this part. There is a resistance, they collide, they transfer the energy, and they increase the vibrations. That's what you need to write when you talk about the heating effect. Sometimes you might also have to write about temperature being directly proportional to the kinetic energy. You'll see this in Unit 5. So because the kinetic energy increases, the temperature in Kelvin is going to increase because of their proportional relationship. Okay. And down here, we have a summary of the things that you need to write. So resistance causes electrode to transfer the kinetic energy to the ions, and they're going to vibrate increasingly, and the temperature increases because the temperature in Kelvin is directly proportional to the kinetic energy. Next up, we need to know the difference between alternating current and direct current. Alternating current is the current whose direction is continuously changing, whereas direct current, the direction is going to be constant in a single direction. So in this diagram, we can see that the voltage, the sign of the voltage is constant for DC, but it is fluctuating and oscillating for an AC supply. Now, just for knowledge, guys, an alternating current has a frequency, and the frequency is basically just the frequency of this wave on the graph. Here is another question from 4PH0 that you can try. We are talking about diodes. And that pretty much is the end of mains electricity. We'll now move on to current and voltage in circuits. The first thing that you need to know is how you put your voltmeters and ammeters. Remember, guys, in a series circuit, there is only one current. So if you want to measure the current, you put the ammeter in series with the component that you're trying to measure. However, in a parallel circuit, the voltage is going to be the same. So if you want to measure the voltage, you put the voltmeter in parallel across the component that you want to measure. And of course, these are our properties of series and parallel circuits. In a series circuit, there's only one loop. In a parallel, there's more than one loop, more than one path. In a series circuit, the current is the same throughout the loop. But in a parallel circuit, the voltage is the same across all loops. So here you can see that the voltage in a series circuit is going to be shared between V1 and V2, but there is only one current throughout I1 and I2, and the I total are all going to be exactly identical. Whereas in a parallel circuit, the current is going to branch off into different parts. So I total is going to be the sum of I1, I2, and I3, but voltage is going to be the same across all of them. So V1, V2, V3, and V total are exactly the same. Now, one thing that I want to mention here is the conservation of current in parallel circuits. This is part of the specification, but it comes up. I think it has only come up like once in the entirety of the exam history. So basically, conservation of current is when the current that goes in is equal to the current that goes out. So in this example, right, the current that goes in is I total, and it is going to be equal to the sum of I1, I2, and I3. These are the currents that are coming out. This is the current that has gone in. So that is called conservation of current. And the reason that conservation of current happens is because charge is conserved. Electrons and electric charge, when they pass through components, they are not used up by the components. They basically just pass through them. So the amount of charge that comes in is the same as the amount of that goes out, and the rate does not change. So the current is also the same. So do bear that in mind. This might come up in your future examinations. Then we look at the advantages and disadvantages of series and parallel circuits. Remember, guys, in parallel circuits, even if one component breaks, others can continue working because they are independent. And in parallel, all components will receive the same maximum voltage. So if you're connecting the components directly to the main supply in the parallel circuit, all of them will get 230 volts. And each component can be controlled independently with its own switch in its own loop. So if you are looking at lighting different rooms and you want to turn off each room individually, you can do that with parallel circuits. In a series circuit, you don't have those advantages. The only advantage that you can get is that all components can be controlled with one switch. So for example, if you're working with decorative lights, you might want to turn all of them off with one switch. You can do that in a series circuit. In a series circuit, you might also need less wiring, but it really just depends. So don't really recommend writing that as an advantage. And of course, we need to look at circuit symbols. We have in total 5, 4, 9, and 5. So we have about 14 circuit symbols that we must know. We have a switch open, switch close, single cell, 2-cell battery. We have a fuse. This is going to be our resistor, a fixed resistor, variable resistor, thermistor, light-dependent resistor, diode, light-emitting diode, LED, lamp, voltmeter, and ammeter. You must know these circuit symbols to be able to solve questions. And yeah, that's pretty much it for chapter 7. Oh, by the way, let's talk about diodes. Diodes, they only allow current to flow in one direction. The direction they flow in is going to be the same as the head of this little triangle. So it's going to flow in this direction. In this direction, LED basically the same function. Very, very high resistance in this direction, so you can't flow like this. Very, very low direction in this, very, very low resistance in this direction, so you can flow like that. The only difference is that they're going to emit light as current passes through, so they can consume a little bit of voltage. Yeah, that's pretty much it for LED and diode. And by the way, guys, LEDs, lamps, they can be used to indicate the presence of current by just looking at them. So if a lamp is on, current is present. If LED is on, current is present. So that's how you indicate the presence of current visibly. Okay, next up, we have electrical resistance. Now, electrical resistance is, as we discussed previously, is a measure of how much electrical current is restricted or opposed It's basically when the electrons collide with the ions in the conductor, which is going to limit the ability to flow freely. Now, we have this equation: resistance is equal to rho L over A. It is not required for international GCSEs, but I think you should know this. The resistance is directly proportional to the length of the conductor and inversely proportional to the cross-sectional area of the conductor. So if the conductor is much thicker, the resistance is going to be much lower. If the conductor is going to be longer, resistance is going to be higher. Shorter, resistance is going to be lower. The way I like to think about it is that if you have more area, electrons can flow more freely. And if the length of the conductor is shorter, electrons only need to pass through a shorter distance, so they don't need to sweat that much. And of course, we have Ohm's law. You must know this. V is equal to IR. When the resistance is constant, the voltage is directly proportional to the current. And the resistance is constant because the temperature is going to be constant. And then we have the inclination questions using Ohm's law. I made a separate video on this, but here is the summary. When we are going from a parallel to the series circuit, we know that the voltage remains the same. However, the total resistance is going to change depending on whether it's parallel or series. Remember, guys, in parallel circuit, the total resistance is going to be much lower, whereas in a series circuit, the total resistance is going to be much higher. So based on that, we are going to explain whether the current is going to be higher or lower and use our equation V is equal to IR with V as the constant. Whereas in questions where we have one fixed resistor with one resistance changing component, what we're going to do is going to talk about how the resistance of that resistance changing component changes and how that affects the total resistance and how that affects the current and how that affects the voltage across the fixed resistor. And if we need to look at the voltage across the component itself, we just take the difference between the battery voltage and the voltage across the fixed resistor. So it's basically going to be the inverse. If it increases across the fixed resistor, the voltage across AC is going to decrease and so on and so forth. Here are some example questions, not from Edexcel, but from Cambridge International Examinations. I think this is from CIE O level, not International GCSE. This is from CIE O level. So you can also check that out to get extra practice. I will have these, the link is in the description. Then we take a look at IV graphs. We should know these and why they look like why they look. First, we have fixed resistor. We basically have current directly proportional to the voltage. This is basically V is equal to IR. And the gradient is constant. Now, the gradient is constant because the resistance is constant. And that is because the temperature is going to be the same in the fixed resistor. Now, in an IV graph, the gradient is going to be 1 over resistance. And that's because, as we know, resistance is V over I. But here, the gradient is I over V. So I over V is going to be 1 over R. So our gradient is inversely proportional to the resistance. So if we have a steeper gradient, we're going to have a lower resistance. If we have a less steep or a shallower gradient, we're going to have a higher resistance. And it also makes sense intuitively because if you have a shallow gradient, even if you increase the voltage by the same amount, the current doesn't increase that much. But if you have a steep one, that's for the same increase in the voltage, the current is going to be increasing much higher. Then we have a filament lamp. It is going to be an S-shaped curve because it looks like an S. Now, in the positive direction, as the voltage increases, the current increases. However, the gradient is going to decrease. Now, the reason the gradient decreases is because the resistance is increasing. Now, why does the resistance increase? Well, because as the voltage increases, the current increases. As the current increases, it causes a heating effect, causing the temperature to increase. So as the temperature increases, the resistance is going to increase, which therefore causes less current increase for the same increase in the voltage. The same goes for the negative direction, but because it is going to be in the negative direction, we're going to have to draw the opposite of this. Okay, next up, we have the diode. As I said, when we look at the circuit symbols, diodes only allow current in a single direction. So in this direction, they are going to have a very, very high resistance, so the current cannot flow in this direction. So they are useful when we want to convert an AC current into a direct current. And the shape is like this, so you will have to actually go a little bit to the positive side before it actually increases significantly, before the current increases significantly. Then we have the required practical where we investigate the relationship between voltage and current for a particular component. It is actually quite easy. So just remember the structure of the circuit. So in this question mark place is where you're going to be placing the component that you're going to test. You're going to need an ammeter to measure the current. Of course, you're going to need a voltmeter to measure the voltage, of course. And you are going to need a variable resistor to change the voltage. So what do? We set up the circuit and then we set the value of the variable resistor to maximum. If this resistance is maximum, the voltage is going to be almost zero. So then what do? We close the switch to complete the circuit. Oh, and by the way, in this diagram, I forgot to draw a switch. So you need to draw a switch. If you don't have a switch, you can't close the circuit, and that's going to lead to some problems that we're going to discuss in the precautions sessions. So what do? We close the switch to complete the circuit, and then we measure the voltage using the voltmeter and the current using the ammeter. And of course, this is going to be 0,0 because our resistance is at maximum. And then we vary the voltage by altering the variable resistor value. So what we do is we just decrease the variable resistor value to start increasing the voltage and therefore the current. And this point is very important, guys. We have to switch off the circuit between the readings to avoid heating the wire too much, which is why we need a switch right here. If we keep it on for too long, it's going to heat up and heat up and heat up, and we can't really look at the direct proportional relationship if it were to exist because our wires are not going to have temperature control. And we also cannot use the full range of voltage, so we cannot maximize the voltage because the current is going to get too high and it's going to lead to too hot of a wire, and it might lead to electric fires. And of course, as usual, to achieve reliable results, we repeat the measurement for each resistance value, calculate the mean, and then we plot a graph, the IV graph, to investigate the relationship. So is it a diode, is it a fixed resistor, or is it a lamp, and etc., etc., and etc. Of course, we have precautions. They might ask you precautions. And the most important thing, of course, is to switch off the current between readings to avoid overheating. And then you can't use too high of a voltage. And of course, you do not need to do not want to touch the wire with bare hands. And you want to check for zero error on ammeter and voltmeter, but these are less significant. So the safety precautions, switching off the circuit, not using the full range of voltage, not using 12 voltage to prevent too high of a temperature. Those are more important. And then, of course, we have an example question from 2019 June paper 1. You can check out the mark scheme so that you can develop your own model answer flow. And this right here is how the taskbook describes it. You can see this on page 77 of your Edexcel physics textbook. The last chapter, guys, it's going to be static electricity. Remember, guys, static electricity is a paper 2 topic, so you only need to revise this for your paper 2. So we have to start with looking at charge. What is charge? Charge is a fundamental property of nature. Anything, well, almost everything, no, actually everything in the universe has charge. If it doesn't have charge, it's because it's neutral, except for neutrons. Neutrons are neutral. So yeah, almost everything has charge except for neutrons. So what kind of charges do we have? We have negative charges and positive charges. And like charges, they attract. Like charges, they repel. We call the attraction, we call it electrostatic force of attraction. We call repelling, we call it electrostatic force of repulsion. Now, Coulomb's law is not required for international GCSE physics, but just remember, guys, that the electric force is going to be inversely proportional to the square of the distance. So as the distance increases, the electric force is going to decrease. And you might need that for some explanation questions. You do not need to know the formula. You don't need to do calculations. And then we have charge formation. You're going to always get a 2-mark question almost at the start of almost every single static electricity question. You're going to get asked, how does this object become positively charged or negatively charged? 2 marks, very simple. If it's positive, it loses electrons. If it's negative, it gains electrons. That alone is going to give you 2 marks. But of course, if you want to be safe, mention friction or rubbing. So because of friction, it's going to lose electron. Because of friction, it's going to gain electrons, so on and so forth. And guys, remember, charge formation only happens when you are rubbing 2 insulators together. You cannot do this when you have 2 conductors rubbing together. And of course, this is just a reminder of what current and voltage are. And in paper 2 static questions, you are going to have to do a lot of calculations using Q is equal to IT and E is equal to QV. So be prepared for that. Remember, guys, Q is charge transferred. So it's going to come in the unit of coulombs, so something like 3.2 times 10 to the negative 6 coulombs. Such kind of values are going to be really, really common. And the voltage is usually going to be very, very high, like 3000 voltages for static questions. And then we have this part. This is actually very, very important. How do you detect electric charge, and how do you know what kind of charge you are working with? Now, the type of question that is actually the most difficult is they're going to make you describe a test to prove that fundamentally we have 2 types of charges. So if you understand this suspended object test concept, you'll be able to answer that. But first of all, we have the pieces of paper method. This is actually the most straightforward one. What do? We just hold the object that we want to test, whether we have charge or not, and then we bring it close to small pieces of paper. If the pieces of paper move towards and get attracted to the object, then the object is charged. The disadvantages of this method is that you can't really know if it's positive or negative. You can only know if the charge is present. Of course, if we have equipment, we can use a coulometer, but if we are asked to describe a method, do not write this because there's no method, you just type it onto the coulometer. The method that I would like to recommend for most questions is the suspended object test. So if you have an object that you don't know is charged or not, you just suspend it with a string and you bring an object with a known charge close to it. So if they repel, it's going to be the same charge as the one with the known charge. If they attract, it's going to be opposite to the one with the known charge. Okay, so we just look for the reaction between those two objects. So are they going to repel or are they going to attract? And of course, this test can be used to distinguish whether the charge is negative or positive, which is why this method is much better than this one. And here is going to be an example question that asks you to illustrate that there are lots of different types of charges. Remember, guys, because we have two different types of charges, we're going to have two different types of reactions. If we only have one type of charge and we bring two objects with the same type of charge, there's only going to be one reaction. So if it's positive, positive, it's only going to be repel. But because we have positive and negative, we have positive, positive repulsion, negative, negative repulsion, and positive, negative attraction. So two types of reactions indicate two types of charges. That's very important. You need to understand that to be able to answer this kind of question. And of course, we look at the uses and the dangers of static electricity. The uses, we need to look at using static electricity in spray or in painting. That's actually the most type of question. You also have to look at inkjet printers and other types of appliances, but you can go take a read for those in your textbook. The type of question that they're going to ask most frequently is about the spray painting using the charges. So they're going to ask you, what advantage do we have? Well, the advantage is that the droplets of the paints are going to have the same charge, and so they're going to repel each other, and that's going to lead to greater coverage because they can move a greater distance, and it's going to lead to an even thin coat because the particles are not going to be clustered in a single spot. And also there's going to be less of wastage because the particles are not going to fall down to the ground. They're going to get attracted to the object. And it can also reach difficult to reach places, such as in these places with the bicycle frame that it's difficult to directly aim with your sprayer. In terms of the dangers, the key thing that you need to know is about sparks. So if something has a electrostatic charge, it's going to want to not have charge. It's going to want to be neutral. So when it is close to another neutral object, it's going to want to give those electrons off. So the electrons, when they get close to a neutral object, usually a conductor, they're going to jump. So in this case, the insulator is full of positive charges. But the conductor, because it is connected to the ground when we have a lot of electrons, the ground can actually give electrons to the insulator. So if the insulator is brought close to the conductor, what's going to happen is that electrons are going to move from the ground through the conductor because it's a conductor, so electrons can move, and it's going to jump across the air to the insulator. And when it jumps across the air, it's going to cause a temporary rise in the temperature of the air, and we can observe that as a spark. Now, the spark, if it happens naturally, in a random place like at your house, near your car, it's fine. But if it happens in places like fuel stations, gas stations, when you're refueling your aircraft, it's going to lead to some problems because when there is a spark, because the temperature is so high, it can lead to fires. So if it's close to fuel and the fuel has a high temperature, even for a few seconds, the fuel is going to start combustion, and that combustion can lead to fires and ultimately lead to explosions. So that's the key concept that you need to know. If you have electrons jumping across two different objects, it can lead to fires and explosions. Here is an example question. This is not from Edexcel. This is also an example question from CRE. So do try it out to expand your question exposure. All right, guys. So that's pretty much it for electricity. In the next video, I'll see you guys in waves. Okay, so next up we have Unit 3, waves. Now, under the unit of waves, we have different types of waves, transverse and longitudinal waves, and we're going to have to look in particular at electromagnetic waves, specifically visible light. And we're also going to have to look at sound waves. And we're going to have to investigate the behavior of waves. So reflection, refraction, total internal reflection, and the Doppler effect. So this first page is to give you a general idea of the key topics in this unit so that you can figure out which topics, which subtopics you need to check off as you go along in your revision. Okay, so let's start with the properties of waves. Now, this right here is a diagram showing two waves. And here we have the wavelength, the amplitude, and other important characteristics of waves that we need to know. So we're going to start with amplitude. Now, amplitude is the maximum displacement of a particle for mechanical waves from a rest position. Now, the rest position is basically the line, the middle line, and we call that the equilibrium line or the resting line. Now, it is the maximum displacement from the rest position. So if we want to find the amplitude on a diagram, which is what we need to do most of the time, we have to measure from the equilibrium line all the way to the crest, which is the highest point on a wave, or all the way to the trough, which is the lowest point on a wave. Next up is a wavelength. Now we can find the wavelength when we are given diagrams where we have the amplitude or the displacement on the y-axis, and we have the distance traveled on the x-axis. So it's a displacement distance graph. Now on these kind of graphs, we can find the wavelength. Now what is a wavelength? Now wavelength is the length of one wave. It can be measured from crest to crest, trough to trough, or it can be measured by looking at one complete wave. Or you can measure it by looking at any two corresponding points of a wave. The easiest, of course, is to look at crest to crest, trough to trough, or sometimes if you can find the exact cycle, you can look at the entire wave. The next thing is frequency. Now, frequency is the number of waves passing through a particular point per second, and frequency basically, therefore, is going to be the number of waves divided by the time taken. Now, that leads us to another topic, another important factor, which is time period. Now, time period is the time taken for one complete wave. Now, we can find the time period on a displacement time graph. So if the x-axis is a time, is given in time, we can find the time period. Now, the relationship between frequency and the time period must be known. It is F is equal to 1 over T, and we're going to have to do computational problems using this formula. So those are the important characteristics of a wave that we need to know. And here is an example kind of question that we can get when it comes to these kind of characteristics. So mostly it's going to be calculation based, and we're going to be giving a graph with the measurements for the y-axis and the x-axis, and we're going to have to figure out the wavelength and the amplitude. Now, do note that the amplitude is going to be given in volts on most of the questions, and that's because we are looking at the traces from an oscilloscope, and an oscilloscope measures the amplitude in terms of voltage. And here is an actual question from a past paper. Now, the link to this file will be down in the description, so you can access this and try this out yourself. Okay, and of course, I also have model answers written in the file as well. So next up is going to be the difference between transverse waves and longitudinal waves. Now, sometimes the question might ask you to draw a diagram as part of your answer. Sometimes it's optional, so just look for the word may. So if it says you may draw a diagram, you don't need to draw a diagram. If your answer is correct, you'll get all 3 marks. But if it says you must draw a diagram, then you have to draw it. So if you have to draw a diagram, this is what a transverse wave looks like. This is what a longitudinal wave looks like. So this right here is a compression. This right here is a rarefaction. You don't need to know those terms. Just know that you have to draw the wave fronts close together and then far apart. Now, speaking of wave fronts, we need to know the definition of wave fronts. It's part of the specification. Now, wave fronts basically mean a line drawn through the points where all the waves are in phase. So that's what a wavefront means. And you can see this in a longitudinal wave. And of course, this needs to be known because it is part of the specification. And in terms of the differences, make sure to state which type of wave you're talking about at the start of your answer. So if you're talking about a transverse wave, make sure to mention in a transverse wave. If you're talking about a longitudinal wave, make sure to talk about a longitudinal wave. Remember, guys, for a transverse wave, the direction of vibration is perpendicular to the direction of energy transfer. For a longitudinal wave, it's going to be parallel. Now, in the place of energy transfer, you can also write in parallel to or perpendicular to the direction of the wave travel. Cool. Next up, we're going to look at the wave equation. Now, the wave equation, of course, is going to be very useful for our calculation questions, very common in all types of wave questions, and the wave equation is V is equal to F lambda. And another thing that we need to have in mind is that V is equal to F lambda is also going to be used for writing our explanations in refraction questions and Doppler effect questions. So in a refraction scenario, we're going to have a constant frequency. So the speed and the wavelength are going to be changing, but in the Doppler effect, we're going to have a constant speed. So the frequency and the wavelength are going to be inversely proportional. So bear that in mind. It's going to become really, really useful once you start tackling explanation questions. Next up, of course, is we have wave behavior. Now, wave behavior is basically just how waves behave. That's exactly what it means. How do waves behave when they interact with changes in media and etc. Now, in reflection is very simple. When a wave reflects, it's going to be reflecting such that the angle of incidence, which is the angle between the incident ray and the normal line, it's going to be equal to the angle of reflection, which is going to be the angle between the reflected ray and the normal line. Now, do remember, guys, in reflection, the medium through which the wave is traveling does not change, and therefore there are no changes to the speed, the frequency, and the wavelength of a wave. In a refraction, however, the medium through which the wave is traveling changes, which is going to cause a change in the direction in which the wave is traveling. It's going to cause a change in speed and thereby causing a change in the wavelength. The frequency of a wave, however, is going to remain constant, which allows us to form a directly proportional relationship between the wavelength and the speed using the wave equation. And of course, we also have to know the equation of the refractive index, which is going to be n is equal to sine I over sine R. And then, of course, we have the Doppler effect in which the frequency and wavelength are inversely proportional, but the medium does not change, and therefore the speed is going to be constant. And of course, we also have total internal reflection, which we need to know, and I'll be diving into that in a few minutes. So here is a deeper look, a more detailed look at reflection and refraction. In reflection, we have identical angle of incidence and angle of reflections. And the ray that starts to come in is called the incident ray. The ray that gets reflected is called the reflected ray. And of course, we have the normal line, guys. Remember, the normal line is drawn with a dashed line, and it is going to be the line that is perpendicular to the surface. And of course, we have no changes in the velocity, in the frequency, and the wavelength of the waves. For refraction, we are calculating n is equal to sine I over sine R to find the refractive index. Remember, guys, because we are using this equation when we're traveling from a region with a lower optical density to a region with a higher optical density, for the same value of the angle of incidence, we're going to get a higher refractive index if the angle of refraction is lower. And of course, if we have to describe what is meant by the term refraction, we can say that it is the change of direction of the rays of light because the speed of the waves are changing. And the reason that the speed of the waves are changing is because there is a change in the medium. And the reason that happens is because the media, the two media, have different optical densities. So here are two scenarios that we can encounter. First one is when we're traveling from a region of low optical density or low refractive index to a region of high refractive index or optical density. Guys, remember, it is if we're going from a low to a high, we're going to have the ray bend away, towards the normal because the speed is going to decrease. If we're going from a region of high density to a region of low density, we're going to have the light ray bending away from the normal. And of course, if we're going into a higher density, the speed is going to decrease, and thereby the wavelength is going to the wavelength is also going to decrease. Whereas if we're going from a high density to a low density, the speed is going to increase, but the wavelength is going to, and the wavelength is also going to increase because V is equal to F lambda, F is constant, and V is directly proportional to lambda. So don't forget to mention your wave equation. Okay, write down V is equal to F lambda. That is going to give you a mark most of the time. So it's going to give you a very, very nice mark for these kind of questions. So that's it for reflection and refraction. Now let's take a look at the Doppler effect. Now the Doppler effect, guys, happens when there is relative motion between two objects, which means that the distance between two objects is getting farther apart or getting closer. Now, for all the Doppler effect questions, these are the points that I would try to include in my answers. So first of all, we're going to talk about whether the wavefronts are getting farther apart or getting closer. We're then going to talk about the change in wavelength and how that affects the frequency. And we're going to explain that using the wave equation, V is equal to F lambda. And of course, we're going to set speed is equal to constant because our medium is going to be the same. And if we are working with sound waves, we're also going to talk about how frequency is related to the pitch. And therefore, if the frequency increases, the pitch increases and blah, blah, blah. And of course, don't forget to name the effect, guys. Okay, if the question does not include the word Doppler effect, make sure to write it down in your answer. It's going to give you a mark. So let's take a look at two examples where the source is moving. So if the source is moving closer to the observer, what's going to happen is that the wavefronts are going to get closer. The wavelength, therefore, is going to decrease because the wavelengths are going to get closer. And because the wavelength decreases, the frequency is going to increase. Why? Because V is equal to F lambda, V is constant, which gives us lambda, or like frequency is inversely proportional to the lambda. And therefore, if the waves are sound waves, we're going to experience an increase in the pitch. So it's going to be a higher pitch sound. The opposite happens if the source is moving away from the observer, the wavefronts are going to get further apart. The wavelength therefore is going to increase, which in turn will decrease the frequency because the speed is constant, V is equal to F lambda, causing a reduction in the pitch. Therefore, this is called the Doppler effect. Next up, we have an example question. You can try this one. It's a 3-mark question. This is relatively easy, and you can already see the wavefronts being shown on the diagram, so you don't need to think much about what's happening. Okay, and of course, we have the mark scheme as well, so you can try it out. Okay, next up is chapter, I believe, 11, which is on the topic of the EM spectrum, the electromagnetic spectrum, guys. Make sure you know which portion of the spectrum lies in which position. Now, the way I like to remember is I like to start with visible light waves in the middle, and I like to go from there. So we know that ultraviolet, ultra means higher, and it's going to be higher than violet. So it's going to have a higher frequency than violet. Now, infra, the prefix infra means that it's going to be lower than something. And because it's lower than red, we know that it's going to have a lower frequency than red. So I like to put it on the right side of red. And because I know that microwaves and radio waves are low energy waves, I'm going to put them to the right side or below infrared radiation. And because I know that radio waves have the longest wavelength, they lie on the furthest right side. And I know that X-ray and gamma rays are, quite dangerous, and so they're going to have high energies, high frequencies, so they lie on the left side. And of course, I know that gamma rays are really are dangerous waves, and so they're going to lie on the furthest left of the spectrum. So that's how I like to remember the position of the different portions of the spectrum. And of course, I remember violet has the shortest wavelength among the visible spectrum, and red has the longest wavelength among the visible spectrum. So the next thing that we need to know, and this is actually the most important part, this is more important than the position of the different portions, we need to look at the uses of each part of the spectrum, and we also need to talk about the dangers of each part of the spectrum. And it's also really good if you can explain how, the uses fit in with the property of each portion of the waves. So radio waves, guys, as the name suggests, we are going to use it for broadcasting, for long-range communication. Why do we use that? Well, because radio waves can be reflected from Earth's atmosphere. So if we're going from the station, we're going to hit the barrier between the atmosphere and the ionosphere, and then it's going to bounce back, something like that. And then we have microwaves. Now, we use microwaves. What do we do with microwaves? We heat food. And of course, we also use satellite transmissions. And the reason satellite transmissions work with microwaves is because the microwaves, unlike radio waves, they don't bounce back. They actually go through the atmosphere to the space stations. And of course, the reason we use microwaves for heating food is because they can go inside the food and make the water molecules excited, which in turn generates kinetic energy, causing a rise in the temperature of the food, which is helpful for heating up food. And that effect is the danger of microwaves. Microwaves can cause internal heating of body tissue. So if you're exposed to microwaves, the microwaves are going to go into internal body tissue, and it's going to generate kinetic energy inside the water molecules, which is going to cause body tissue to heat up, which can lead to a variety of diseases. Infrared radiation, guys, infrared radiation, we use it to cook food. Why? Because infrared radiation is the transfer of thermal energy in radiation form. So we use it to cook food. And we also use it for thermal imaging and night vision equipment. It's also used in optical fibers. Now, the reason we use it in optical fibers is because infrared radiation can easily undergo total internal reflection. It has the critical angle that we need to be able to transmit in those thin optical wires. The danger of infrared is that it can cause skin burns, and that's because, like I said, it is the transfer of thermal energy in wave form. So if you're exposed to heat for too long, you're going to burn your skin. Visible light, guys, it's used for photography, and of course it's used for seeing, it's used for vision. But if you expose yourself to too much visible light, it might cause some kind of damage to the retina. Ultraviolet light is used for killing bacteria in water purification. So if you do human biology, you would know that ultraviolet light is essential in the last and final stage of sewage treatment for killing the remaining bacteria. It's also used for security markings on banknotes. You can use it for checking the legitimacy of your money of cash. Now, the reason we can use it for killing bacteria is because it is highly ionizing, and the reason we can use it in security markings is because the security markings will only show up when exposed to UV rays. The danger, of course, is that the UV rays can damage your skin cells by damaging DNA, leading to mutations, and therefore causing cancer. X-rays, well, we're very familiar with that. Medical X-rays are used to check for broken bones, to check for internal body structures, and we also use it for security checks at airports. Now, X-ray, the reason we use it for looking at the inside of the body is because they can pass through soft body tissues such as, skin and muscle, but they cannot pass through bones. Just like ultraviolet, X-rays can also damage cells, leading to mutations and causing cancer. Gamma radiation is very, very useful for sterilizing medical equipment. It's very useful for sterilization. Now, once again, if you do human biology, you will know that sterilization is one of the top methods of food preservation. It kills bacteria due to its ionization property. However, just like the other two parts of the spectrum, it can cause mutations. Okay, so that's pretty much it for the electromagnetic spectrum chapter. If you have a gist of this table, you'll be able to answer most questions. Here is a sample question. Now, this question is from the sample assessment material, so feel free to try it out yourself. Of course, we have the marking scheme as well, so you can cross-reference it. Next up, when it comes to light rays, guys, we have to look at refractive index. So how do we find the refractive index of a particular material? Well, if we are investigating a glass block, what do? We put it on a piece of paper. And then we use the ray box to shine a single wavelength of light. So it's a single color. So we either use red light or green light. The reason we use red light or green light is to prevent dispersion. If we use, for example, white light is going to cause dispersion, so it's going to separate into different colors. We can't really measure the angles anymore, so we have to use monochromatic light. Now, once we shine the ray of light, what we do is we are going to mark the path of the ray of light that is going into the ray that is going into the block, and we're also going to mark the path of the ray that is coming out of the block. So we're going to do that by using our pencil. So we're going to mark the crosses and we're going to trace the path, and we're going to measure, we're going to draw a straight line using a ruler. So using a ruler is going to be very important. And of course, once we are done with that, we're going to have to turn off our ray box. The reason we turn it off is to prevent heating. Remember, ray boxes can be quite dangerous because they produce monochromatic light. They can cause some heating. Okay, once we are done with that, we're going to have to draw a outline of the glass block. We're going to have to draw an outline of the glass block, and the reason we have to do that is because we're going to have to make measurements of the angles, so it's going to become useful when we measure the angles and draw the normal. Now, once we are done with drawing the outline, we remove the glass block and we draw the normal lines, so it's going to be something like this. These are our marked lines. This is our outline. We're going to draw the normal here, and then we measure the angle of incidence, and then we connect the two lines. So we're going to have the incident ray. So this one is the incident ray, this one is the emergent ray. We connect them together. This one is the refracted ray. So here is our normal, here is angle of incidence, here is angle of refraction. So we measure those using a protractor. Now, once we use the protractor, we can find the exact values, but we cannot calculate right away, because if we calculate right away, it's not going to give us a reliable and accurate value. So what do? We measure the angle of refraction and the angle of incidence by varying them. So a very succinct way to put that is to say measure angles of refraction for different angles of incidence. If you say it like that, you can get the mark point in as concise of a manner as possible. And of course, we're going to draw a graph of sine I against sine R. So we're going to have sine I on the y-axis, and then we're going to have sine R on the x-axis, and we're going to calculate the gradient, which is going to give us a refractive index. That method is going to be tremendously more reliable than just using the table and calculating the mean, and it's also much faster. And of course, they also let you ask you what kind of equipment you need. So the equipment you need, guys, is going to be the ray box, the pencil, the ruler, and the protractor. So those four keep in mind. This right here is an example question, I believe, from 2024 November. So make sure you practice this and look at how the mark scheme puts the words together so that you can reference it to write your own model answers. Okay, guys, now let's take a look at total internal reflection. Now, total internal reflection, the first thing you need to know is the definition. Now, the definition is going to be very simple. Just look at the term itself. Total means all of the light rays. Reflection means are reflected. Now, internal means that it's going back into the medium in which it was traveling. And of course, it happens at the boundary between two different media. So, what is our definition? Well, the definition, guys, is that total internal reflection happens when the rays are traveling from a medium with higher density to a medium with lower density, and the angle of incidence is greater than the critical angle, and therefore the waves are reflected back into the first medium. Sorry. Sometimes they also like to ask you specifically the conditions required for TIR. So if you are asked about the conditions, make sure to answer these two. So let's take a look at this diagram. So in this diagram, we can see the incident ray and the refracted ray. So because the angle is still much smaller than the critical angle, we're still going to have refraction. But as we increase the angle of incidence and as we reach the critical angle at this point, we're going to see that the light ray refracts with an angle of refraction of exactly 90 degrees. So once you exceed the critical angle, we are going to get our total internal reflection, of course, following the law of reflection. And of course, guys, remember the definition of the critical angle. The critical angle is the angle of incidence for which the refraction is 90 degrees. I believe that this is actually the best, most concise definition to write. I think you can also write the angle of incidence above which total internal reflection occurs, but I just prefer this definition because it's more precise. And of course, we have to do calculations using sine c is equal to 1 over n. And it is always a good thing to remember at least two different uses of total internal reflection. So I like to remember optical fibers for communications with our infrared rays and prismatic reflectors for safety. So the things that we put on our bicycles and cars so that when light from behind hits the vehicles, they get reflected and the driver from behind can see what's in front of them. So that's pretty much it for total internal reflection. Now let's move on to the last part of waves, which is going to be sound waves. Now, first of all, the thing that you need to know is that sound waves are longitudinal waves. This means that they have different parts called the compression and the rarefaction. Once again, you do not need to know these terms. I'm just saying them so that you have an intuitive understanding of what sound waves really are. And of course, in compressions, we are going to have a high pressure region, so air molecules are going to be compressed. Whereas in rarefactions, the pressure is going to be low, the air molecules are going to be spread far apart. And the transverse wave model for sound waves is basically the graph of pressure against the distance. So in high pressure regions, we're going to have our crest. In low pressure regions, in rarefactions, we're going to have our trough. So that's important because we need to be able to understand the nature by which sound waves are transmitted. To be able to answer questions such as explain which medium in which sound waves travel the fastest. Now, to be able to answer the question, you need to know that sound waves travel when vibrations between particles are transferred to adjacent particles. So the answer to this question would be solid, and that is because sound waves travel by vibrations, and in solids, the particles are tightly packed, so the vibrations can be transferred from one part of the solid to the another part more effectively, causing a faster travel of the waves. And we also need to know the range of frequency of human hearing, which is from 20 hertz to 20,000 hertz. Sometimes you're going to have calculation questions and you're going to have to calculate the frequency of a wave, and then you're going to have to deduce whether that wave can be heard by humans. The only thing that we need to do is to compare it with this range. So if it's if it's below 20 hertz, we're going to say it is too low. It's below 20 hertz. It's too low. Humans cannot hear it. If it's above 20,000 hertz, we can say it's higher than 20,000 hertz. It's too high of a frequency. Humans cannot hear it. Something like that. Then we have two different investigations / practicals. First one is a speed of sound question. Sometimes you don't have to design the entire investigation. You have to look at the design of the study, sorry, the design of the investigation given in the question, and you're going to have to critique, different parts such as the way that they measure the distance, the time taken, the human reaction errors. But if you understand the optimal setup, you're going to be able to answer those critique questions quite easily. So how do you set it up optimally? Well, first of all, you want to stand 100 meters away from each other. 100 meters is the minimum. If it's less than 100 meters, sound waves are going to reach the other person too quickly. And if it reaches too quickly, you're going to have a hard time starting and stopping your stopwatch, which is going to ruin the accuracy of your timings. And of course, with the experiment should be done in still air. If it's not in still air, the waves are gonna travel away. You're gonna have some loss, so the timing is just not gonna be correct. And when we're measuring the distance, make sure to use a measuring tape or a trundle wheel. Do not use a meter ruler because you cannot measure over uneven terrain with a straight ruler. Because, for example, if this is a cliff, then you can only put your ruler like that. You can't measure like that. So no ruler, trundle wheel, or measuring tape. And now comes the method. The method is going to be clapping two wooden blocks together. Now, some people like to write about clapping two wooden blocks together and that getting reflected. Now, that's also okay, but I think that two people standing apart is just much more straightforward to describe in exam scenarios, which is why I recommend this approach. Now, when the other person sees the visual cue, that is the wooden blocks being clapped together, what do? They start the stopwatch. When the sound waves reach them, when they hear the sound, they stop the stopwatch. And of course, to achieve reliable results, what do? We repeat the entire test and calculate the mean value. And if we repeat again and again, it's going to minimize the margin of error caused by human reaction. And of course, if we increase the distance between the two people, it's also going to decrease the significance of human reaction time error because the timing because there's going to be much more time for the person with the stopwatch to react to the sound waves reaching them. And last but not least, we can calculate the speed using the equation speed is equal to distance divided by time. Just like we did in the refractive index calculation question, what we can also do is we can also plot the graph of distance against time. So we're going to use we're going to use a variety of distance values. So 100 meters, 110, 120, and etc., etc. And we're going to plot the time taken values, the mean time taken values for each of them. And we're going to draw a graph through those points. And we're going to calculate the gradient, which is still going to give us the speed. So that's also an alternative method, which will definitely produce a much more reliable value. Then we have the frequency of sound waves. The frequency of sound waves, this rarely appears, but it is part of the specification. So you must know this practical. Now, what do we do and what kind of equipment do we need? Well, we need a microphone and an oscilloscope. So the majority of this practical is really all about setting up the oscilloscope so that you can get the measurements that you need to get. So what do? We connect the microphone to the oscilloscope and then we adjust the oscilloscope to get a steady trace. Now, oscilloscopes, they do not give a steady trace right away. You'll have to adjust some settings in order to get that waveform steady so that you can do your measurements. And then we'll have to adjust the time base on the oscilloscope so that it shows a minimum of one cycle. So for example, if we have a sound wave with a low frequency, we might not see the entire wave on the screen. So we're going to have to adjust the time base. The time base is basically just a measure of how much time is represented by one square on the x-axis. So if we have a time base that is much higher, we can fit in more waves within one screen. And then what we're going to do is we're going to count the number of squares for multiple cycles. The reason we count the number of squares for multiple cycles instead of one cycle is because one cycle might not exactly fit a certain number of squares. So for example, it could be something like this. So if it's something like this, we can't tell how many squares this is because this guy is not exactly on these lines. So we're gonna have to count for multiple cycles, and then we redivide it to get the time taken for one square, which is gonna give us the time period. And of course, we have to multiply with the time base because the number of squares does not exactly represent 1 second. So for example, 1 square might be 0.004 seconds, so we have to multiply with 0.004 seconds. And then we use the equation of is equal to 1 over t to calculate the frequency to get us the frequency. And of course, when we are dealing with these kind of questions, oscilloscope questions, we're gonna have to work with 10 power negative something something because it's usually going to be 0.00 something something seconds. So make sure you get your power of tens correct. Don't blunder your power of tens because you will end up losing a mark even if the integer in front is correct. Alright guys, that's pretty much it for waves. In the next video, I'll catch you in Unit 4, Energy. Thank you, bye-bye. Unit 4, Energy. Energy is the ability to do work. Now, under that topic of energy, we have energy transfers and the conservation of energy, Sankey diagrams, efficiency, thermal energy, conduction, convection, and radiation. This is particularly the most difficult, the most varied and difficult type of questions under Unit 4. And then we have energy resources, the easiest because you just memorize a bunch of advantages and disadvantages. So starting with the types of energy stores. You should know this by now. You don't need to know every single one, but you should have an intuitive understanding of what these energy stores mean. Energy transfers, this is actually very important because you're going to see this question type in a variety of contexts, in a variety of scenarios. So you need to know these kind of methods. You need to know these methods. So first of all, we need to know that there are 4 different methods with which energy is transferred from one store to another. And by the way, guys, the concept of energy stores is very important. In full page 1, you cannot say light energy, heat energy. You can't say sound energy. You have to discuss in terms of energy stores. So energy, think of energy stores as a bucket and energy as water. So thermal is the bucket and the amount of energy you have in it is the water. Okay. And if you're transferring water from one bucket to another, you can do this in 4 methods. You can do this mechanically, in which a force is involved. So if you're pushing an object and you're transferring energy from your chemical energy store, your hand, to the kinetic store of that object, you're doing it mechanically for force. If an object is falling down from a high place and it's gaining kinetic energy, it's losing gravitational potential energy. So energy is being transferred from GPE to KE. That is being done mechanically. Why? Because it's accelerating downwards. Why is it accelerating downwards? Because of gravitational force or weight. So that's mechanically. Electrically happens in circuits. So if we're doing anything that involves circuits, energy is being transferred electrically. And then we have biheating. Now, biheating refers to conduction and convection. So if we're transferring thermal energy, for example, throughout a hot kettle, that's going to happen by heating. And then we have biradiation. This happens when we have waves and infrared radiation. So if thermal energy has been transferred from a hot stove to your skin, that's going to happen by radiation. So you need to mention what type of energy transfer is involved in every single energy transfer. And if you're answering energy transfer description questions, use this method, okay? So first of all, say that the initial energy store decreases and that the next energy store increases. So for example, if we're going from gravitational potential energy to KE, say that GPE decreases and KE increases. And then say that it transfers from GPE to KE by a method. So it would be mechanically. So what do is we describe the energy transfer from store A to store B, that store A decreases and store B decreases, and then we also need to mention the method. And of course, remember to mention the object that you're talking about. So if it's the kinetic energy of the ball, talk about the ball. If it's the thermal energy of the ball, talk about the ball. If it's the thermal energy of the air, talk about the air. Make sure to be specific to get your marks. So here's an example. We have a drop right at an amusement park. So it's going to drop from a high place to a lower place. And it's going to ask you to describe the energy transfers immediately before the car was released to when the car has fallen 18 meters. So at the top, what do we have? We have energy in the GPE store. So GPE store is going to be maximum. And because we are stationary, it's going to be KE is going to be 0. No energy in the KE store. But as it falls downwards, guys, energy is going to be transferred from the gravitational potential energy of the right to the kinetic energy of the right mechanically, because work is being done by the gravitational force or weight. And because there is work being done by the weight, energy is also going to be transferred from the gravitational potential energy to the thermal energy of the right. But actually, this is because of air resistance. So it's kind of, you can also say that it's because work is being done by the air resistance. So it's going to transfer some of the energy in the GPE store to the thermal store of the right. So the right is going to get hot, but it's not going to stay on the right forever. It's going to transfer from the right to the air. So thermal store of the right to the thermal store of the surrounding air. How? By radiation or by heating. So if you look at the mark scheme, we can get a mark for mechanically. We can get a mark for saying that it transfers by radiation from thermal of the right to thermal of the surrounding air. And then we can talk about gravitational to kinetic store. And then we talk about thermal to the thermal store of the surroundings. So that's how you answer a typical energy transfer question. Next up, we have conservation of energy. Very, very important. You don't, more often than not, they're going to ask you to apply it rather than define it, but it's always a good idea to understand what it is. So conservation of energy is the statement that energy cannot be created or destroyed. Now, this is the conservation of energy. This is the principle. This right here is the result of that principle, of that truth. What is the result? The result is that the total input energy must always be equal to the total output energy. This results from this right here. And so if we break down the total output energy, we can break it down into useful output energy and wasted output energy. Because remember, no system on Earth is ever 100% efficient. So there will always be some kind of wasted energy. And of course, in some questions, when you have to calculate with this, just mention that when you're using the conservation of energy, you might get a mark for that. And then we have efficiency. Efficiency is a measure of how efficient, how much of the input energy is actually useful. So you can do useful input energy divided by total input energy or total output energy. It doesn't matter. Both of these nominal values are going to be the same because of conservation of energy, and then multiply with 100%. Now, sometimes you don't need to put the percentage. You can also show it as 0.87 instead of 87%. It's fine in the mark scheme. And then we have Sankey diagrams. Now, Sankey diagrams, guys, students, they struggle a lot with Sankey diagrams. And that is because they do not have a precise, specific mental model that they are following when they are drawing a Sankey diagram. So make sure you read these steps and apply it with your consciousness. So think about it, okay? The first step, guys, we determine the scale. So how much of a length is going to represent how much of an energy? You have to do that if it is not given in the question. If it's given in the question, you don't have to do it. And if the question gives you a grid for drawing the Sankey diagram, you can do it in terms of squares. 1 square is probably going to be 1 centimeter. Next, another thing that you need to take care of is that if the question doesn't really tell you the exact energy values, you might have to calculate the exact energy values so that you can do this scale thing. The first step after that, when we actually start drawing the diagram, is to draw the width of the diagram, which represents the input energy. Always start with the width of the input energy. And then we draw the width of the area representing the useful output energy, and then we draw around it. And then we draw the width of the area representing the wasted output energy that is facing downwards, and then we draw it. So the reason I write and draw it and draw it is because we actually just start with measuring out and planning the width of the arrow before we actually finally draw it and seal it in place. And of course, guys, do not forget your labels. So let's look at an example, okay? In this example, we are given this scenario. In a handheld fan, so a handheld fan like this one, 30% of the energy is transferred electrically from the chemical store of the battery, so the battery is down here, to the kinetic store of the fan blades. So these guys are going to be moving. So 30% of that goes to the kinetic store. So this is going to be moving. The rest is transferred to the thermal store of the air. Draw a Sankey diagram for this situation. So how will we draw it? Now, first of all, we know that 30% is useful. So how much is wasted? Well, we just do 100 minus 30. That gives us 70%. And then we have to determine the scale. So because we have very, very, very good numbers, of course, it is the middle of the question, we can just do 1 centimeter represents 10%. So 30% represents 3 centimeter, 20%, 7, 100%, 10. So our input width is going to be 10 centimeters. And I am going to start by drawing the input width, guys. Okay, I'm going to start by drawing the input width. It's going to be 10 centimeters, so that's going to be 10 squares. Now, I'm going to draw it in this kind of shape. So because my wasted arrow is going to come down, I'm going to leave some space for the wasted arrow. And because my useful arrow, I can extend it as much as I want. I'm just going to extend it a little bit over here. So that's the shape that I'm starting with. Then we look at the useful arrow. So we look at the width of the useful arrow. How many centimeters are we working with? We're working with 3 centimeters. So how many squares? We draw 3 squares, seal it in place. And then we plan the width of the wasted arrow. So for the wasted arrow, I'm gonna calculate 1, 2, 3, 4, 5, 6, 7 squares. Now, if I'm drawing it in real life, of course, I'm gonna have to use my pencil. So if I don't have enough space for 7 squares, I'm gonna erase a bit of this part and make sure that I have 7 squares. And then I'm gonna protrude this part and then seal the rest of the arrow. And of course, we finish it up with our nice labels, and that gives us a full mark Sankey diagram. Okay, guys, so this is how you should be drawing your Sankey diagrams in the actual exam. Should you draw curvatures? Personally, I would not do curvatures. It's it's an extra headache. So just this method should be fine. Make sure you get your measurements right. Make sure you get your labels right, and you should be good to go. So make sure you practice that mental model, that exact sequence of steps to really, get the right shape of the diagram. Next up, thermal energy. Now this chapter is it's actually really difficult. All you can do is master the basics. You can't really prepare for the questions because the question range is immense. So first of all, what is thermal energy? Thermal energy is a sum of all kinetic energy stores and potential energy stores in a system. Just try to understand it. Don't need to memorize it. That's what thermal energy is. And the most important part is to link thermal energy to the kinetic energy of the molecules and the particles within the system. Which is why in Unit 5, you'll see that the temperature and Kelvin is directly proportional to the kinetic energy. Okay, so that's what thermal energy is. Okay, and by the way, guys, thermal energy, you cannot call it heat energy because heat, the word heat refers to the transfer of thermal energy. So saying heat energy is like saying that the energy of the transfer of heat energy, which doesn't make sense. Okay, so don't say heat energy, it has to be thermal energy. So thermal energy is transferred from one object with higher temperature to another object with a lower temperature. And we're going to look at the concept of thermal equilibrium. So for example, here we have a 90 degrees Celsius object and we have a 25 degrees Celsius object. And these two blocks are going to be in a closed system. So energy is not going outside, it's closed. Okay, it's closed. So because we're going from 90 degrees Celsius to 25 degrees Celsius, it's going to transfer energy like that from 90 to 25. So after some time, okay, what happens is that both of these blocks are going to reach the same temperature. So it could be 60 degrees Celsius. Now we call that the state of thermal equilibrium. There is no more net energy transfer between these two objects. So that's also quite important. There are some very difficult questions that utilize the concept of thermal equilibrium, even though it's not explicitly taught in international GCSE physics. So make sure you have a little grasp of that. Right. Then we have thermal energy transfers. Of course, guys, we have conduction, convection, and infrared radiation. So you need to be able to describe how energy is transferred in conduction and convection. Now, in conduction, guys, in both conduction and convection, guys, we are working with particles. So, of course, being able to describe it is really important. Now, this is a summary table. We'll go into a little bit more detail. I think. Oh wait, no. Here is conduction. Yeah, here is going to be convection. So we'll go into detail in a few slides. So here is an overview. Conduction happens in solids, convection in fluids only. Now, can fluids conduct? Yes, they can, but they are poor conductors. Why? Because particles are far apart from each other. We'll talk about the mechanism later. Can solids undergo convection? No. Why? Because solids cannot have particles move. Infrared radiation is just a part of the EM spectrum we discussed in Unit 3 previously. All objects will emit infrared radiation as long as the object has a temperature above 0 Kelvin. So when we're working with solids, think about conduction and infrared radiation. When we're looking at fluids, think about both convection and infrared radiation and a bit of conduction. So it depends on the type of question that you get. So, if you see solids, if you see fluids, this is what to think about. And by the way, guys, conduction can happen through a solid as well as from solid to solid. So as we saw previously, it can happen when two blocks are touching each other, and it also happens when it's going through the same block. So if it's going from a hot end of a block to a cold end, that is also conduction. So remember, guys, conduction, two objects or single object. Convection, however, does not happen through two objects. It happens through a single fluid mixture. So that's also a nuance to really understand about. So here's an example. I found this on Save My Exams of a mug. So a mug is going to transfer thermal energy to the surrounding air, right? And also to the table. So if you're touching the table, it's going to transfer in conduction. So hot object to cold object. Two objects touching each other, solids, conduction. To the air, it can transfer by convection or radiation. To the sides, it's going to transfer by radiation. But because there is air upwards, what's going to happen is that it's going to heat up the air above a little bit. The air is going to expand and rise, and it's going to lead to convection. So this is a very good way to visualize, conduction, convection, and radiation. So now let's take a look at the details of conduction, guys. Conduction, you need to be able to describe this, very, very important. You can write this in terms of electrons or atoms, but I prefer writing in terms of atoms because I just feel like it's more intuitive. So when we look at atoms, okay, conduction through a solid. At the hot end of the solid, guys, the particles are going to gain kinetic energy because they're being heated by a source. And because they gain kinetic energy, they're going to vibrate with a greater amplitude, and the vibrations are going to also happen much faster, much more frequently. So when they vibrate, they're going to collide with the neighboring particles, and they're going to transfer the kinetic energy to the neighboring particles. So the neighboring particles get kinetic energy, they vibrate faster, they collide, and they can transfer, and so on and so forth. So the vibrations are going to be adjacently transferred to the neighboring particles, and this happens to the solid, and that's how conduction happens. However, that alone is not enough to transfer energy quickly. In an insulator, that's all you can do, vibrations. But in a conductor, conductors such as metals, they have free electrons. So because we have free electrons, what we can do is that the free electrons are able to move around. And because the electrons are moving around, they also carry kinetic energy. And when they carry the kinetic energy, they're going to move faster. And when they move, they're not moving freely. They're going to collide with the atoms, the ions in the metal lattice, and they're going to collide with other electrons. So when they collide, they're going to give off the kinetic energy that they were carrying. So at the hot end, they're going to carry a lot of energy, kinetic energy, and then they're going to transfer that as they move along to the colder end. So you can also describe it in terms of free electrons. Whatever you prefer, both will be accepted by the Maxim. And of course, guys, all solids can conduct thermal energy, but conductors, such as metals, can do so much more quickly because they have lots of free delocalized electrons, which can transfer kinetic energy much, much more quickly because they are actually moving, not just vibrating about fixed positions. And of course, this one, we see this in a few questions. I think the last one I saw was in 2023 June paper 2 or paper 1. It's about factors affecting the rate of conduction. So when we're looking at things like gloves and thick gloves, right? They're gonna ask okay, why do thick gloves stop conduction? So you need to know this to be able to answer those questions. First of all, state of matter, solids conduct the fastest, we know that already. Type of material, conductors, free electrons, conduct better. And thickness, this is actually very important, guys. Longer materials or thicker materials are going to conduct more slowly because the electrons are going to have to move from this end all the way to this end. If it's very thin, it's just going to have to move from here to here. So thermal energy transfers much more quickly. And then surface area, if the surface area is much greater, conduction is going to happen faster. Why? Because we have more electrons, more particles, more vibration, faster electron vibration. And then temperature difference, if there's a greater temperature difference, then conduction is going to be much faster because the particles on the colder end are not going to be very, very active. So the transfer of kinetic energy can happen much more frequently without bumping into them in the first place. Then we have convection. This is actually very, very easy. If you're Burmese, your life is just much better because we can just memorize this. Make your life much easier, mnemonic. But of course, if you're not Burmese, then you just have to know that when it gets heated, it expands and it becomes less than, and the fluid rises up. The words that I have underlined in red, they are the most important ones, so do not forget them. And of course, if we are having to describe a complete convection current, a complete cycle, don't forget to say that the colder denser air sinks in to replace the hot fluids, and that process repeats, forming a convection current. Make sure to name that. It's going to give you a mark. Right, thermal radiation, not much to say except for the types of objects. Shiny white objects are poor absorbers and poor emitters of IR radiation, but they can reflect it very, very well. Whereas on the other hand, dull matte black objects are better emitters and better absorbers, but they are poor reflectors, which is why if you wear black shirts on a hot day, it gets much hotter because you're absorbing the infrared radiation instead of reflecting it. So if it's hot, wear something white, wear something of a lighter color so that the waves can get reflected. And one tip that I would like to give, guys, is to use your comparative degrees. Guys, always use comparative degrees. Nothing is absolutely best, okay? Something is just much better than something. So always use the word better or poorer instead of saying it's good, it's bad, okay? Comparative degree, always the way to go when you're answering these questions. Then we have reducing thermal energy transfers. This is actually very, very important. So I want to remind you guys of how certain things work in terms of energy transfers. And if you understand this, you can actually apply this in many, many scenarios. So we're going to take a look at fur because it actually has a variety of ways of reducing thermal energy transfer. So fur, okay, first of all, before we dive in, fur is actually white. So it's going to reflect inwards, right? It's going to reflect the thermal energy back into the body. Second of all, fur can trap air because there are little spaces between them. So when air is trapped, it cannot move. If it cannot move, it cannot form convection currents. If it cannot form convection currents, it's going to reduce the thermal energy transfer by convection. Second of all, air itself is an insulator. Remember, guys, air is a fluid. So particles are far apart. They cannot vibrate with each other. They cannot conduct. So air is an insulator. So what that's going to do is that it's going to reduce conduction. And fur itself is an insulator. So because we have two insulators, we're going to reduce conduction again. And therefore, it is going to reduce the thermal energy loss from the body. So guys, when you are investigating, okay, how thermal energy is reduced, don't just look at one thing, look at multiple things. Is it an insulator? Do we have trapped air? Can we form convection currents? Do we have white materials? Do we have black materials? Investigate everything. It's going to give you the marks that you need to rank up to grade 9. So here's an example of a vacuum flask. So vacuum flask, also very, very smart. You have an insulator as a stopper, which reduces the convection of it, reduce the conduction. And then you have trap air, prevent convection currents, and of course air is an insulator, reduce the conduction. And because there is a vacuum there, no particles, so no convection, no convection. And then we have silver walls of glass, so it's going to bounce back the waves. So if waves come like this, go back into the T or whatever you're putting into it. And of course, guys, remember to think about the direction of energy transfer. So, okay, some students, they do this automatically. Some students don't even think about it. So think about this in the first step, okay? Where are we going? Where is the energy going? Is it going to T to the surrounding or the surrounding to the T, okay? Think about that direction first before you talk about how energy loss is minimized. Right, next up, the chapter, work done, power, and the stuff. So this chapter, very, very short, lots of equations, starting with work done. Work done is basically just energy transferred. If it's mechanical energy transfer, we just multiply the force and the distance over which the force is applied, you get work done. So yeah, work done is equal to energy transfer. In some questions, they will ask you like, okay, calculate the energy transfer, you get the value, and then in the second question, they're gonna ask like how much work is done. You just basically copy paste the same value, 3 mark, right? And then we have power. Power is the rate of transfer energy, or the power is the rate of which work is done. So just do work done divided by time taken, or energy transferred by time taken. We see this in electricity as well. Very, very easy. Then we have kinetic energy. Kinetic energy is the energy possessed by moving objects. So all moving objects has kinetic energy. If it accelerates, kinetic energy goes up. If it doesn't accelerate, kinetic energy remains constant, and so on and so forth. K is going to half mv square. Make sure you use that. Don't forget to square your speed value. Minus a mark because you're not getting the correct answer. Then we have GB is mgh. Very, very easy. Just look at the relative height. Put that in, put the mass in, make sure the mass is in kilograms, not in grams. If we're working with balls, guys, okay, balls are always in grams, guys. Look at balls, okay, balls are always in grams. If it's in grams, convert into kilograms. Don't forget, very, very important. I think this is a funny story. I think even in my actual exam, like when we finished physics paper 1, I saw many students coming out like, oh my god, I forgot to convert the mass of the ball into kilograms. So like, guys, balls, anything like light and soft, kilograms, please, okay? And then we have energy transfers for a falling object. This is just another illustration. We also did that in energy transfers. So GPE to KE, sum goes to thermal. And at the bottom, we have no GPE. And of course, we have KE maximum at the bottom. And I mean, if it doesn't bounce back, if it doesn't stop, it's going to be KE maximum at the bottom. And remember, guys, conservation of energy, GP is equal to KE plus thermal energy. Right, the last chapter, but also the biggest content in terms of content heaviness. Energy resources. So energy resources split into renewable and non-renewable energy. Renewable means it will not run out. Non-renewable means it cannot be replaced or run out. So just split that, know the definitions, and then look at the fossil fuels, nuclear fuels. We have oil, gas, and coal on the fossil fuel side, and then we have nuclear fuel, uranium, plutonium, enriched uranium, blah 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 blah. And then we have renewable energy, sun, wind, water, geothermal. I just split it like this because it's much more convenient. Under the sun, we have photovoltaic cell, and then we have solar heating. So we use solars, but it's not PV cells. It's solar, different type of solar. We use it for heating. And then we have wind energy. We have wind turbines, water energy. We have wave energy, tidal energy, hydropower, electric stations, geothermal energy, heat under the ground. So these are the type of energy that we're working with. And of course, here is the specification point so that you know what you need to work with. And of course, guys, energy resources is a paper 2 topic. Don't forget, don't revise it for your paper 1. Waste of time. Okay. So anyway, for the fuel, high energy density, we know that just need a little bit of it. It can go a long way. Do not depend on the weather, you just need to get it from the ground. Easy. Disadvantages, carbon dioxide, not good for global warming. And of course, it will run out one day. So, I mean, 50 years later, we might not have it anymore. Then we have, what is this? Nuclear fuel. Nuclear fuel, guys, this is actually a Unit 7 topic. You'll understand this more when you learn Unit 7. But basically, high energy density because you don't need that much for fusion. And does not cause pollution because fusion doesn't release anything except for like water and, radioactive waste. But of course, the problem is we have radioactive waste. We have barium, kryptonium, radioactive, not good. We can't just throw it into the dustbin. We have to store it properly. So we have problems with long-term storage. Where do we put it? What do we build? Facilities? Thieves? Dangerous, right? And then we have risk of nuclear accidents, of course. We have reactor meltdown problems. For example, Fukushima. We also have Chernobyl. Name it, get a mark. And of course, it's non-renewable. So even if we don't need a lot, we might run out one day. And of course, it's something that people will have to fight over. Demand and prices and politics and stuff. Not really good. And of course, for Unit 7, guys, you need to know your fission versus fusion differences. So make sure that you know the differences between fission energy and fusion energy and why fusion energy is much better. Next up, hydroelectric power. Hydroelectric power, guys, is actually like one of the best energy resources because it's renewable, doesn't produce carbon dioxide, it's always available, and you don't need to transport your fuel because you just need to put the water down. And hydroelectric power can respond to changes in demand. So I think, there you go. Hydroelectric power can quickly respond to changes in demand because you just need to control how much water is flowing down every minute. The disadvantage is like it's not that much of a disadvantage, but if you look at it from an environmental perspective, it's actually kind of bad. The first one is that you have to use a large area of land. So if you look at this image, right, it's almost like a river that this power station takes up. It's a lot of land, and land is not free, guys. Okay, you can use land for like agriculture, building houses. So if you are going to just flood it, you can't do anything with it anymore. So that's a problem. And of course, we also have animals and the natural habitat. We can't, if we just take their home, they're gonna die. They're gonna go extinct. So it's a problem as well. And of course, number 3, they are location dependent. You can just build it anywhere you want. You can't just build it in the middle of the city because we need a mountainous area because we need water to flow down from a high place to a lower place. So we need a mountainous area. If you don't have a mountainous area, you can't build it. Sorry. So yeah, the common pattern that you're gonna see in renewable energy is that they often don't produce carbon dioxide and they're renewable. So these two are actually very, very repeatable. But of course, if the question already says renewable, guys, you cannot write it again in your answer. Do mind that, okay? Solar. So solar, we're talking about photovoltaic cells. Photovoltaic cells, again, renewable, no CO2 gases, available in almost all locations. You want to put it in the city, put it on your rooftop. You want to put it in the suburban location, put it on your rooftop. It's fine. But it doesn't always work. You can't do it at night because there's no light, and you can't do it when it's cloudy. You can't do it when the weather is not good because there's not enough light. So it depends on the amount of sunlight available. It depends on the amount of daylight hours. That's a disadvantage. And of course, it also takes up a lot of space. As you can see in this diagram, it's a whole entire solar farm. I mean, like, that solar farm could be an actual farm to feed people. But no, we just have solar panels. So land use is quite a problem. Next up, geothermal. Geothermal is actually also really good, but because it's renewable, does not depend on the weather. So it doesn't matter if it's if it's raining or sunny, you can get it. And comparatively speaking, it requires less space because it's more of a humble structure, and more of the structure goes underground than on land, so you get more on land space. But it can cause polluting gases, and it can pollute groundwater because, like I said, you have to build it. Most of it goes underground, so the processes can pollute groundwater, which can lead to some water problems. And of course, it is location specific. You have to assess the ground for production of natural thermal energy. If there's no natural thermal energy from the decay of radioactive substances underground, you can't really do it. So it's also location specific. You can't just build it anywhere. Next up, we have demand. Okay, demand. The concept of demand is also actually quite important because we have to think about how quickly we can respond to changes in demand, and that's gonna be a big topic that we have to discuss when it comes to which type of energy resource is better. This is also why thermal hydroelectric power stations are actually still quite the gold standard of energy resources because they can just respond to changes in demand really, really quickly. So if you don't have that much demand, you can just reduce it, prevent energy loss. And if you have high demand, you can respond to it. So that's why hydroelectric power are good. So basically, electricity demand is basically what it means. It's how much electricity we need to the pedestrians are using, the cities are using. So if we have higher demand, we need to use more. So we need to increase our production. If we can't increase our production, some houses will not get electricity. If we can increase our demand, there's also a question of if we can increase our production, there's also a question of how quickly we can do that. If it's gonna take half a day, it's not really ideal because we want electricity in the morning, right? But we can't get it by noon, so that's all gonna be a problem. So we have to think about that. So yeah, think about electricity demand when you're just discussing the resources. And of course, our hydroelectric power stations are still going to be the gold standard because it's like one of the fastest response. And I think fossil fuel stations are also quite relatively slow compared to HEPs. Okay, then we have wave and tidal power, guys. Wave and tidal power, they are. I think they came up during my exam. Yeah, they came up during 2025. They come up also during 2023, but not as common as like HEPs and solar powers. But still, you should know. So how does wave power work? Basically, it comes from the kinetic energy of the wind, the wave kinetic energy, and then the turbine kinetic energy. Advantages, renewable, no CO2 emissions, same thing here and here as well. But the problem with wave power and tidal power is that both of them are location specific, and the wave power depends on the weather because waves come from wind, right? So if it's not windy, there's not a lot of waves. If it's not a lot of waves, you can't do a lot of energy. And both of these, tidal power and wave power, they are going to damage the aquatic wildlife because we're gonna build them inside, we're gonna have to build them underwater. So it's gonna damage aquatic wildlife, not good for the environment. And comparatively speaking, tidal power can respond much more quickly to demand, but still it's not as good as HEPs. And then another advantage of tidal power is that the available times are predictable because, of course, we have a high tide and a low tide daily. We can predict when the high tide and the low tide are going to be happening. So available times are more predictable, much better. Yeah, that's pretty much it for wave and tidal power. Let's move on to the next one, which is going to be the wind farms. Wind farms, they're actually quite good, but also quite bad. I mean, disadvantages, renewable, no pollution. You can build them as long as there's open space. It doesn't have to be mountainous. As long as there's open space away from people, it's fine. But they depend on the weather a lot. So if it's not windy, it's not gonna work. And they can cause harm to a migrating flock of birds. So if birds run into them, birds are gonna die. And it's gonna cause some population loss. And of course, we have noise pollution. They're quite noisy. I mean, just take a look at this fan. It's noisy, right? I mean, this is just a mini fan and it's already noisy. So if you have a giant fan the size of a skyscraper, it's not going to be very pleasant to listen to. And of course, visual pollution. I mean, visual pollution is quite a debatable one because some people think it looks nice, some people think it looks ugly. So I don't really recommend writing that in your exam. The key thing is that it's a dilute source of energy. Now, dilute means that it's not concentrated. Not concentrated means it has a low energy density. So for the same amount of hours, let's say 3 hours of being exposed to wind, it's only going to generate like, I don't know, 100 megawatts, 100 megajoules. Whereas, if we did a HEP for the same 3 hours, we can generate, let's say, 300, megajoules. So yeah, it's not generating the same amount of energy to the same time. And of course, because of that, it's very difficult for the energy output to meet the demand. So if you're trying to power a whole city with a wind farm, you might not be able to do it. And of course, still large areas of land and location specific. We cannot build it near cities. We cannot build it near roads and stuff. We need open space. Okay, we need open space. All right, I think that's pretty much it. Yeah, that's pretty much it for your energy resources. Here as an example question. Remember, guys, when we are answering, make sure to split it into advantages and disadvantages. Especially for a 4-mark question, I need to split it into advantage and disadvantage for one source, advantage and disadvantage for other source. And of course, guys, I cannot repeat this enough. I cannot emphasize it enough. If you're comparing two things, use comparative degree. Okay, don't say one thing is absolutely the worst at something. Okay, say this one is worse than the other. This one is better than the other. Okay, make sure to use your comparative degrees. That will help you a lot. All right. I think that's pretty much it for your energy resources. Here is another example question. Yeah, that's pretty much it. And here's the specification summary for Unit 4. As you can see, specification-wise, it's not very long. The only thing that's going to trouble you in Unit 4 is the variation of the questions. So energy transfers, thermal energy transfers, you're going to see them in a variety of contexts. So like, like I gave examples of, you're going to see things like fur, you're going to see things like clothes, you're going to see things like, vacuum flasks, you're going to see racing cars, you're going to see, there's just a bunch of stuff. So make sure you have a fundamental understanding and make sure that you're able to apply your knowledge in a variety of contexts. And of course, guys, do not panic when you're writing your responses. Okay, do not panic. Keep calm. Do your best. Write as much as you know. Connect, your theory. Connect your understanding, and just apply and butcher the mark scheme words, okay, the technical words, the physics words, to get your marks. Don't just write based off your intuition and feeling. Write using your mark scheme words, technical words, and that's gonna make your life a lot easier in terms of anxiety, and it's also gonna help you land a higher chance of getting those mark scheme words. So yeah, that's pretty much it for Unit 4. See you in Unit 5. Unit 5. There is a good balance of things to memorize, things to calculate, and things to think about. So let's get straight into it. Unit 5 has two parts, density and pressure, and solid, liquids, and gases, or kinetic theory. And of course, under density and pressure, we have density and pressure, pressure for solids, pressure for liquids. And we look at solids, liquids, gases, things like change of state, specific heat capacity, and of course, ideal gas molecules. And we cannot forget our absolute temperature scale. So let's get straight into density. What is density? Density is a measure of mass per unit volume. It's indicated by the Greek symbol rho. It's equal to m over v. The standard SI unit is kilograms per meter cubed. So you're going to have to do calculations with that formula. Next up, we need to look at how we are going to measure the object's density. So this is going to be the most frequent question that you're going to see when it comes to density. How do we measure the density of an object? For a regular object, it's very, very simple. First of all, just start by thinking about the formula. So our formula is density is equal to mass over volume. So we have to measure mass and volume to get density. So how do we measure mass? Well, we use an electronic balance. And how do we measure volume? Well, because it's a regular object, we have a definite formula for the volume of that object. So all we need to do is take the measurements that we need. So for example, if it's a sphere, right? If it's something like a sphere, if it's spherical, we use the formula V is equal to 4 over 3 pi r cubed. So the measurement that we need to do is the radius. So how do we measure the radius? We use a vernier caliper. Now, vernier caliper is this equipment. By the way, this diagram is from Save My Exams. This is a vernier caliper. It has these two teeth kind of things. So if you are measuring something circular, you can measure the diameter and thereby the radius much more accurately than if you were to use, a ruler. So once you get your radius, you calculate your volume using your formula. And once you get that done, you can get your volume. So once you get your mass and your volume, you can calculate your density. But of course, if you want to get reliable results, you wouldn't want to repeat that multiple times and calculate a mean. So here is an example question about hailstones. So you can check that out. Okay, next up, we have an irregular object. Now, an irregular object is going to be a little bit more complicated, but it's still quite easy. And the reason is because you do not have an exact formula for the volume. So mass, still the same, you do your electron balance, but for the volume, you will have to use a displacement method. Now, in order to do this, you can use a measuring cylinder or a beaker, but the most optimal way to do this is to use a Eureka can because it is specifically designed for the displacement method. So first of all, you have to fill your Eureka can with water to the spout. So before it reaches the spout, so we're going to fill it up to this level. And what you're going to do is you're going to drop the object, very, very gently. And that is important because you do not want to splash water. If you splash water, you're going to lose volume. If you lose volume, your measurement of volume is not going to be accurate. Next, we need to completely submerge the object in water. So if this is our Eureka can, we want to make sure that the object is completely underwater. That way, we make sure that a sufficient volume of water gets displaced from the Eureka can. Next up, we have to measure the volume. So you can put the measuring cylinder underneath the spout and you can measure the volume using your measuring cylinder. Now, when you are using a measuring cylinder, there are a couple of precautions that you should know. First of all, always measure the volume at eye level to avoid parallax error. And of course, make sure to read the volume value at the bottom of the meniscus and make sure you're placing your measuring cylinder on a horizontal surface to get an accurate volume measurement. Okay, now once you get that, we can basically say that the volume of water in the measuring cylinder is equal to the volume of the object. And of course, if you're just using a measuring cylinder, so if you're just having a measuring cylinder and you have an initial volume, you will have to subtract again. So this is the initial volume, place the object, it goes up, so you subtract and find the difference. You could also do that, but it doesn't really work for larger objects. And another thing that you need to take care of is you need to measure the mass before you measure the volume. And that is because if you're working with objects such as rocks, these things can absorb water. So if they absorb water, the mass is going to increase. So it's no longer going to be the accurate, actual dry mass of the rock. So make sure you mention that as well. And of course, as usual, repeat and calculate the mean to get reliable results. So here is another question. Now, this is a question about using your calculation and your displacement methods. This question is from 2025 June paper 1 PR, the exam that I did. So do check this out. Yeah, this is kind of a novel question style. So this is actually a good question to study. Yeah, that's pretty much it for this density. Let's move on to pressure. Now, pressure is also a very, very simple topic. So first of all, we have pressure. What is pressure? Pressure is force per unit area. So this is actually very important. You need to have this intuitive understanding, to understand further advanced concept when it comes to pressure. So understand that pressure is force per unit area. So it's basically just force, but you restrict it to 1 meter square. So of course, the unit of force is going to be Newton per meter square, which is equal to 1 Pascal. Now, that is for solids, right? In solids, we have the surface area, we have the force, we can calculate it. But in fluids, we don't always know the surface area. So we have a new formula. We have P is equal to rho hg. But guys, remember, okay, P is equal to rho hg is basically, it's exactly the same as P is equal to F over A. Pressure is still force per unit area. The reason we do that is because we know density, we know the depth, and we know the gravitational field strength. It is much easier to use those values instead of finding the force and finding the area. So intuitively, the concept of pressure is still the same. And of course, I've also written down how we derive the equation of pressure here. And then guys, some properties that you need to know, this is actually very, very important. Pressure acts equally in all directions. So in the liquid, it does not matter, which direction you're looking at. Pressure acts equally in all directions. The only difference that's going to happen is depth. So as you go deeper in a fluid, the pressure is going to be much higher. And the reason is because there is more fluid above that depth. So there's going to be more weight pressing down. So for the same unit area, there's more force, which means that the pressure is higher because pressure is force per unit area. And of course, pressure does not depend on shape or surface area. This also comes down to that intuition that pressure is equal to force per unit area. So if it's 1 meter square, the force is going to be the same regardless of how big the overall surface area is, because you don't care about how big the overall surface area is. All you care about is 1 meter square. And 1 meter square is going to be the same kind of force, the same value of force. So you can measure the atmospheric pressure using the barometer. And atmospheric pressure is basically the pressure that is exerted by the atmosphere when you're at sea level. It is 100 kilopascal or sometimes 101 kilopascal, or sometimes you will see it as 10 power 5 pascals. And when you're doing calculations with containers that don't have an open top, you have to take into consideration atmospheric pressure. So the liquid pressure is rho gh, and the atmospheric pressure is going to be 100 kilopascal or whatever is given in the question. So if you want the total pressure at the bottom, you have to combine rho gh with the atmospheric pressure to get the total pressure. So don't forget to add your atmospheric pressure, guys. Then we have Pascal's law, which is pressure transmission in fluids, but this is basically just a repetition of this guy. Pressure acts equally in all directions. The Pascal's law states that pressure is constant in a liquid. So this is useful in piston mechanisms. such as this one. For example, if we are pushing down with the force of F1 and we have a cross-sectional area of A1, well, we know that the pressure is going to be constant, so P1 is going to be equal to P2, right? The pressure going down here is going to be equal to pressure going up here. So we get this equation F1 over A1 is equal to F2 over A2. But because area 2 has a much higher surface area, the pressure, the force exerted by piston Y will also have to correspond to the larger area by increasing the force. And so basically what we get is we have the same pressure, but we get a larger force. So the input force is low, but we can get a higher output force. This is useful in things like brake systems in cars. So this is a question that I've popped up before. So make sure you understand the concept of pressure transmission. But the key thing really is just this: pressure acts equally in all directions. Okay, that leads us to chapter 19, I think, which is solid liquids and gases. Now, solid liquids and gases, guys, we have kinetic theory. This is actually very, very important. And of course, this page you can also use for your 4CH1 questions. So solid liquids and gases. So the way I like to teach my students and the way I like to memorize as well is to break down the facts into two parts. So break it down into arrangement and motion first, and then break arrangement down into how close the particles are and what kind of pattern the particles have. And then move and break down motion into how the particles move and how fast they move. So in solids, the particles are very, very close, very tightly packed, whereas in liquids, they are just touching. In gases, the particles are very, very far apart. Okay, what kind of pattern do solid particles form? They form a regular pattern. Liquid particles, they form an irregular pattern. Gas particles also irregular, means there's no pattern. You can also say it's a random pattern. Now, when it comes to motion, how do particles move? Well, in solid, particles cannot move. They can only vibrate about a fixed position. So there is no displacement. In a liquid, however, the particles can indeed flow or slide past over each other, but they are not moving very, very freely. In a gas, they can move very, very freely in all directions, however they want to move. How fast do particles move? Well, in solids, they can't move, so this does not apply. However, in liquids, they move quite fast, but not as fast as gases. Gases, however, can move very, very rapidly because of their high kinetic energy and because there are also no forces of attraction keeping the particles stuck to each other. Then, of course, comes to this part. Now, this part, guys, is actually very, very important. Please make sure to memorize this. The mark schemes are quite strict and specific when it comes to this part. This part is basically how state changes occur. So this is also part of the specification. You need to be able to describe the changes that occurs when state change occurs. So first of all, let's take a look at the changes that occur when a solid melts. So when a solid is going into a liquid. So the way I like to structure my responses and the way I like to structure my memorization is that I like to think about the structure and the arrangement and the motion before and then after, and then I like to talk about what happens during, and then I like to combine them together into this concise writing. So in a solid, right, particles are regularly arranged and they can only vibrate about fixed positions. But afterwards, in the liquids, they can now slide past over each other. They now have an irregular arrangement. What happens during the state change? Well, the bonds between the particles are broken or weakened. I prefer the words weakened because we still have some bonds left in a liquid, and the particles move further apart from each other. So this is what happens during the state change, and this is the overall change in the arrangement and the movement. And then combine them together. Okay, bonds are weakened or broken during the state change, which causes the particles to move further apart from each other. At the start, they can only vibrate, but now they are free to move because this happened, and they can now slide past over each other, and the particles can turn from regular to irregular arrangement because of these changes. Same goes for when the liquid boils. I like to talk about what happens before. So liquid, this kind of thing happens, but in a gas, they can now they are now very, very far apart and they can now move rapidly and randomly and freely in all directions. Why? Because the bonds between the particles are broken and the particles with the highest kinetic energy, they can escape from the liquid surface. So I like to combine that into particles move further apart from each other because the bonds between particles are broken and the particles escape the liquid. They can now move more freely and randomly, and they can now, the structure is now very irregular. There's no more noticeable pattern. So this part gonna be very important. Usually you see this on paper 2, but you might also see this on paper 1, I think. Okay, next up, heating and cooling curves. This is also important because this part is important. Students often forget this part, and that part is that when state change occurs, temperature is constant. The temperature does not change. Why doesn't the temperature change? Well, because the kinetic energy does not change during state change. Now, why does that happen? Well, because temperature in Kelvin is directly proportional to the kinetic energy. Okay, because kinetic energy does not change, the temperature also does not change. There have been 3-mark questions in the past where we have to explain this part, so make sure you are able to find the link between temperature and kinetic energy and explain and describe this properly. And of course, they might also ask you, like, okay, what is happening during this horizontal section? And you can say it is changing from, for example, here, it's changing from a solid to a liquid, and here it's changing from a liquid to a gas. And then we have to also talk about the gradient of temperature time graphs. So the gradient of the temperature time graph is actually temperature, the change in temperature divided by the time taken, right? And later we'll see that the specific heat capacity is PT over M over delta T. So basically, the specific heat capacity is the power, okay, the energy supply rate divided by the mass of the object times 1 over the gradient. So if the gradient is higher, the specific heat capacity is actually going to be lower. So that is why we have different gradients when we change from a solid to a liquid. Because in a liquid, the specific heat capacity is much lower, whereas in a solid, the specific heat capacity is much higher, which is why the gradient is less steep. So please take care of that as well. Haven't seen this in recent questions, but if they want to up the difficulty a little bit, it can come up. And of course, we now have specific heat capacity. Guys, specific heat capacity, please memorize it in this form. Students like to memorize it in delta Q is equal to MC delta T, but I think this form is much more intuitive, and easier to understand. And also it helps you memorize the definition of specific heat capacity. The specific heat capacity is that delta Q divided by M delta T. Delta Q is the amount of energy that is supplied, M is the mass of the object, and delta T is the change in temperature. So you can basically just use this formula to memorize the definition. So specific heat capacity is the amount of energy needed to raise the temperature by 1 degree Celsius of a 1 kilogram mass, which is why it is delta Q over M over delta T, basically like that. And of course, the unit is joule per kilogram per degree Celsius or joule per kilogram degree Celsius. Now comes the big part. How do you determine the specific heat capacity of a material? Well, think about this formula first, okay? And guys, please take care when you are doing the specific heat capacity experiment. Don't write delta Q is equal to MC delta T because you are finding C, not delta Q. So make sure you make C the subject, okay? So first of all, I like to think about the formula and then I like to break it down, okay? So first of all, how do we find the amount of energy needed? Well, the amount of energy needed we can find using the equation E is equal to IVT, right? So we will know the current using the ammeter, we will know the voltage using the voltmeter, and we can measure the time taken using our stopwatch. How do we measure the mass? We use the balance. How do we find the temperature change? We measure the initial temperature, the final temperature, and subtract. We measure it using a thermometer. So basically, it's just that written in a list. So first of all, what do? You find the mass. If it's a solid, you can just put it on an electronic balance. But if it's something like liquid, what do? You find the mass of the beaker, and then find mass of beaker and the liquid, and then you find the difference to get the mass of the liquid. Then you put your thermometer in, find the initial temperature, and then you start your heating, and then you find the final temperature, and you find the difference, okay? Increase in temperature is equal to final minus initial. Use voltmeter to find the voltage, ammeter to find the current, and of course you have to start your stopwatch when you start heating, and then stop it once you stop heating to get the time taken. And you calculate your energy using E is equal to VIT, and you determine the specific heat capacity by using the equation C is equal to delta Q over M delta T. So delta Q from here, M from there, delta T from here. So basically just use the equation as a guide to make sure that you have ticked off every single variable that you need to know to be able to calculate your specific heat capacity. And as usual, repeat the entire experiment and calculate your mean value. Here is an example mark scheme so that you can reference your model answer against this so that you can ensure you get your full marks. And of course, the last part, guys, ideal gas molecules. Ideal gas molecules, very, very easy to memorize. First of all, you need to know how gases cause a pressure in the container. Gas particles, they move randomly, they collide with the wall of the container, and they produce a force, and pressure is force by unit area. So because there's a force on an area, there is pressure. Very, very easy. Move randomly, they collide, they cause a force. Pressure is force per unit area, which causes pressure. Now, you can write P is equal to F over A, but sometimes the marking scheme, if it gets strict, they say things like P is equal to F over A alone is not enough. So make sure you write pressure is force per unit area in words to really, really secure that single mark. And then we have our ideal gas law, okay? Ideal gas law is P is equal to nRT over V. You do not need to know this equation until your A levels, I think. The only thing that you need to know is how volume and pressure are related and how temperature and pressure are related. So let's take a look at volume and pressure first, okay? Now the formula is P1V1 is equal to P2V2. You need to know this to be able to calculate your values. And the concept is that the pressure is inversely proportional to the volume, which is why pressure is equal to K over V. So you get PV is equal to K, which is why we can do infinite PVs to do your calculations. Okay, so how do we explain, okay, changes in pressure when there's a change in volume? Well, when the volume increases or decreases, right, the particles are going to get farther apart from each other or closer to each other depending on the change. Because the walls of the container are getting farther apart or closer together. Now, when the walls get further apart, let's say, there are less frequent collisions with the wall because the walls are farther apart, particles are farther apart. And therefore, the average force produced per unit time decreases. So they collide less frequently, the force per unit time is also going to be less frequent. And because pressure is force per unit area, because force decreases, the pressure will also decrease. Because pressure and volume are inversely related, inversely proportional, the pressure is going to decrease. And of course, the contact area will also decrease if you're looking at, the if you're looking at a decrease in the container. If you're looking at an increase in the container, the contact area will also increase. But this is not necessary. If you're able to write the top part, you will get full marks. Now, before we move on to temperature and pressure, we need to look at absolute temperature scale. So Kelvin temperature is the absolute temperature scale. The lowest possible temperature of the universe is 0 Kelvin. If you want to convert from Kelvin to degree Celsius scale, you do Tk is equal to T degrees Celsius plus 273. Basically, temperature in Kelvin is always going to be greater than temperature in degrees Celsius because there can be minus 270 degrees Celsius, but then there can never be a temperature lower than 0 Kelvin. So Kelvin is always going to be a natural number. Okay, now to understand absolute temperature, by the way, absolute zero is the temperature at which the pressure and kinetic energy of particles are zero. Theoretically, practically, it's not really possible. So if you have a graph of pressure against temperature, and you're asked to find the temperature, absolute zero temperature in degree Celsius scale, all you have to do is extrapolate it back, and then the point where the y-axis value is zero is when you reach the absolute zero temperature. So temperature and pressure. Now, temperature and pressure, guys, are directly proportional. So is pressure directly proportional to temperature in Kelvin, which gives us P is equal to K times T. So we get P over T is equal to constant, which allows us to do infinite P over T's. So our formula is P1 over T1 is equal to P2 over T2. And of course, your unit must be in Kelvin. So if the question gives temperature in terms of degrees Celsius, you have to convert to Kelvin first before you can plug this into your formula, which is why these calculations often go for 3 at least and sometimes 4 marks. So how do you explain changes in temperature and pressure? Well, temperature and pressure is directly proportional to the Kelvin temperature. So if the temperature increases, the particles will have higher kinetic energy. And because the kinetic energy increases, they can move more frequent. They can move faster. Because they move faster, they collide with the walls more frequently. And the collisions are much harder, much more forceful. And so the force per unit time increases because pressure is equal to force per unit area. Because the force increases, the pressure will also increase. And because the pressure increases, we're going to increase a higher pressure. So yeah, that's pretty much it for ideal gas molecules. How does volume affect pressure? How does temperature affect pressure? We have two formulas. Know your absolute zero temperature, know your absolute temperature scale. How do you convert from degrees Celsius to Kelvin temperature? And of course, how do gas molecules exert a pressure? So yeah, that's pretty much it for Unit 5. It is definitely the easiest chapter because mostly memorization, mostly calculation, some thinking, but even the thinking doesn't get that difficult. So yeah, I hope you have a blast with your revision. See you in Unit 6. Hi guys. So we're now entering Unit 6 territory. And by the way, I don't know why, but it's it's physically impossible for this guy to stand upright. Anyways, we're now entering Unit 6 territory, and we're gonna have to do the entirety of Unit 6 in one sitting. So make sure you grab a nice cup of water. And yeah, let's start Unit 6 revision. Unit 6 breaks down into two parts, magnetism and electromagnetism. Now, magnetism is the foundation of electromagnetism, so make sure you get your magnetism theory right. So under magnetism, we have things like magnetic materials, induced magnetism, investigation. Now, induced magnetism, guys, is quite important. And then we have electromagnetism. How do we construct a simple electromagnet? We have right-hand grip rule, left-hand grip rule for motor effect. And then we have electromagnetic induction or degenerator effect. And then how do we use that in the transformers? So let's get started right away with introducing what a magnet is. Now, a magnet, guys, is a material that can attract or repel other magnets, that can attract magnetic materials, but they do not have an effect on non-magnetic materials. Now, you need to know some examples of magnets. First of all, we have permanent magnets. Permanent magnets will forever retain their magnetism, and they are made with hard magnetic materials, for example, steel, nickel, cobalt. And we have temporary magnets. These are things that, such as induced magnets. So induced magnets are basically magnetic materials that temporarily become a magnet because they are in a magnetic field. And we have electromagnets, where the passage of current leads to the formation of magnetic fields around the current carrying conductor. And we'll look into this in detail in a few slides. So those are some examples. Now let's take a look at how magnets attract magnetic materials. Now magnets attract magnetic materials by inducing magnetism, and this therefore causes a magnetic force between the induced magnet and the actual permanent magnet. So in this diagram, you can see we have a magnetic material close to an actual magnet. Once it gets close to the actual magnet, the magnetic material becomes a magnet temporarily, and we call that induced magnetism. So we have poles being induced, thereby causing magnetic force, which causes the magnetic material to become attracted. Now let's take a little more detailed look at what magnetic force is. So magnetic force is exerted in a region of space around a magnet, and that region of space is called the magnetic field. The magnetic field is a finite region of space in which the magnetic force of a magnet can act. Now magnetic fields cannot be seen using our bare eyes, so we visualize them using magnetic field lines. Now magnetic field lines, we have a few important properties to note. First of all, magnetic field lines, they never cross, but they can interact. So if they overlap, they become stronger, the magnetic field becomes stronger. If they cancel out, there is no more net magnetic field. And the density of the magnetic field lines is proportional to the magnetic field strength, and thereby how strong of a magnetic force is exerted. So the closer the magnetic field lines, the stronger the magnetic field is. And then of course we have to look at the interaction between different poles of magnets. As we know, unlike poles attract, now how do they attract? Well, they attract because their magnetic fields interact. So this guy has a magnetic field, this guy has a magnetic field. Those magnetic fields interact or overlap, leading to a stronger magnetic field, causing the two magnets to get attracted to each other. And then we have, of course, like poles, they cancel out, and we draw in such a way. And of course, when they cancel out, we have this point, which is called the neutral point. There is no net magnetic field there. Cool. So next up, the magnetic field strength. Okay, the magnetic field strength is actually the greatest near the poles, and this is of course indicated by the magnetic field lines being very, very close to each other. There being a high density of magnetic field lines are close to the poles. And another vocabulary that I would like to introduce here is the use of the term polarity. Now, polarity is the same as the direction of a magnetic field. Okay, so pole refers to the north and south poles, and polarity refers to where the north and south pole is. So in this diagram, we can see that the polarity is north pole is on the left and south pole is on the right. So if we say the polarity reverses, that means that the north pole will go to the right and the south pole will go to the left. So that's a vocabulary that we would use of we will find great use of in later chapters, such as in the generator effect. Okay, so that's a very basic introduction to magnets, magnetic fields, and the magnetic force. Now let's take a deeper look at magnetic materials. Of course, guys, in the universe, there are two types of materials, magnetic materials and non-magnetic materials. Magnetic materials can be attracted by a magnet, whereas non-magnetic materials cannot. Examples of magnetic materials that you should know include iron, steel, nickel, and cobalt, maybe neodymium if you can remember 5 instead of just 4. Non-magnetic materials, everything else is non-magnetic. You can just memorize it like that. Now, there are two types of magnetic materials. Magnetic materials further branch into two types: soft magnetic materials and hard magnetic materials. Very easy to memorize the definition of this, guys. Soft magnetic materials are materials that are easy to magnetize and easy to demagnetize. Now, magnetized, guys, basically just means you are turning a magnetic material into a magnet. So for a soft magnetic material to become a magnet, it is easy, and for it to lose that magnetic property is also very easy. So if you write these 2 points, you're going to get 2 marks. And an example of a soft magnetic material that you should know is iron, and it is used in the construction of electromagnets as well as in the soft iron core of transformers. Now, iron is going to become very, very useful when we look at electromagnetism. Hard magnetic materials are the opposite, so they are difficult to magnetize and they are also difficult to demagnetize. The implication of that is that hard magnetic materials, once they are magnetized, they will retain their magnetism for a long time. Examples include steel, nickel, and cobalt, and they are of course used in permanent magnets such as horseshoe magnets and bar magnets. Now, often you will also see soft magnetic materials being described as magnetically soft and hard ones being described as magnetically hard, still the same meaning, so you can write the same definition. And of course, this is a further exploration of magnetic fields. As I said before, magnetic field lines never cross, they can interact, and the stronger the magnetic field, the closer the magnetic field lines are. So you need to be able to draw magnetic field lines around a bar magnet. Keep in mind they should never cross. Okay. And of course, magnetic field lines always go from North Pole to South Pole. Okay. And toward S-wind. Next up, we have uniform magnetic field. Now, uniform magnetic field, you will be required to draw them and you will be required to know how you can create a uniform magnetic field. And it's also good to know what a uniform magnetic field is. So a uniform magnetic field is a magnetic field whose magnetic field strength is constant. So if you have a uniform magnetic field, it doesn't matter where you place your magnetic material, it's going to experience the same force. Now, how do you draw a uniform magnetic field? Well, you draw two opposite poles and you connect them using straight lines, parallel lines that are equally spaced or evenly spaced. Now, how do you create a uniform magnetic field? You basically just bring together two bar magnets close together with opposite poles facing each other. If you write this, you're going to get 2 marks. Now, diagrammatically speaking, this is your uniform magnetic field example. The lines are straight, the lines are parallel, and they are evenly or equally spaced. And of course, you have two opposite poles of a bar magnet. Now, if you have if you have like poles, however, the magnetic field lines are going to be cancelling out. Remember, guys, they are going out like this in an outward fashion. And of course, magnetic field lines come from N, go into S. So make sure you get your arrow directions correct as well. Okay, so that's pretty much it for the magnetic field. Next up is our required practical. This is actually very, very common and you'll often get 2 to 3 marks for this question. So there are actually three ways in which this question can come. They could ask you to describe a method to determine the pattern of the magnetic field, or they could ask you to determine the shape of the magnetic field on itself or the direction on itself. If it asks for pattern, you need to write for both shape and direction and it will often go for 3 or 4 marks. However, if they only ask you for shape, just write for shape, it will go for 2 to 3 marks. If it's direction, just write only for direction. So how do you determine the shape? Well, what you do is you sprinkle iron filings on paper. The word is sprinkle, nothing else. The reason is sprinkle is because you are putting down a few amounts and you're spreading them over. So sprinkle is the best word. Okay, do not say pour because pour means you're dumping them in large amounts. That's not going to work. And of course, you have to use iron filings. Then you gently tap on the paper or the card and the iron filings will move to show the shape. This will get you 2 to 3 marks easily. If it's direction, you have to use your plotting compass to find the direction. So use plotting compasses and you want to position them in such a way that they form continuous lines. So the head of the arrow must be pointing towards the tail of the other arrow on the other plotting compass. And if you do that correctly, the needles will line up to show the direction of the magnetic field and you can draw that on your paper to determine the direction of the magnetic field. Remember, if they're asking for pattern, you will have to answer and describe how you find the shape and then how you find the direction. And then we go back to induced magnetism. So the question is going to ask, okay, there is a magnetic material. For example, let's say we have an iron ball, and then the iron ball is placed close to a magnet. Okay, so and the question is going to ask, explain why the iron ball moves towards the magnet, why it is attracted by the magnet. So this is how we have to answer. We'll have to answer in terms of induced magnetism. So for example, we have this block of iron and it's going to be placed close to the North Pole. Now, once it gets placed close to the North Pole, it is going to become magnetized. Okay, the iron is going to become a magnet, temporarily speaking. And when it becomes a magnet, of course, it's going to gain polarity. So the South Pole is going to be close to the North Pole and the North Pole is going to be opposite. So it's going to become, the poles are going to become induced in the iron. And because the magnetic field of the temporary magnet, this guy, and the magnetic field of the permanent magnet, they overlap, there's going to be a magnetic force, thus causing the iron to become attracted to the magnet. So the lines that I have written in red, they are going to be important for your exam. And then we move on to electromagnetism. Now, electromagnetism, guys, we could say it's a phenomenon, but so at iGCSE level, we could just say it's a phenomenon because there's a truth. There's a principle. Something is happening, and we need to memorize the fact that it is happening. Okay, we don't really need to know why it is happening at iGCSE level. So electromagnetism, it is the phenomenon that for every current carrying wire, there is a magnetic field around it. And if it is a straight wire, the shape of the magnetic field is going to be circular. So in this diagram, we can see that for a straight wire, the magnetic field is going to be circular. And the direction of the magnetic field depends on the direction in which the current is being carried. So how do you find the direction of the magnetic field and the shape of the magnetic field? Well, you can use the practical method, okay? if you use a practical method, what you do is you cut a very, very small hole through a card or a piece of paper and you connect your wire through it, and then you sprinkle your iron filings to get the shape, and then you use your plotting compass to get the direction. But of course, this is not very convenient. This is not fast. So what do? You use your right hand bend grip rule. Bend grip rule is a very, very fast and easy way of finding the direction of the magnetic field given the current or vice versa. Okay, it's a tool that we use to find it. So in figure 6.7, we can see that the person applying the right hand grip rule. So what do? You grab your right hand. Your thumb represents the direction of the current in the wire, whereas your other four fingers represent the direction of the magnetic field. And of course, it is going from north to south. However, there are other variants of the right hand grip rule as well. For example, if we are working with not a straight wire, but a wire being coiled into a circle, how do we use the right hand grip rule? Well, we just flip what the thumb and the other fingers represent. So if we are working with a solenoid or a coil, the thumb is going to point towards the north pole of the magnetic field, whereas the other four fingers are going to represent the direction of the current in your solenoid. And of course, you should also know how you are going to draw the field lines for these wires. So for a flat coil of wire, it's basically the same as a bar magnet. We have a central straight line, and then we have other lines curving, and then of course circular magnetic fields around this portion where it's almost straight. For a solenoid, you just repeat that with more lines because because we have more turns, the magnetic field strength is greater, so we reinforce that using more lines, and it's pretty much the same as a bar magnet. And here, right, is a summary of your right hand grip rule. So for a straight wire, thumb is current, but for solenoid, thumb is the v direction pointing towards the north. Then we have this question. You will see this quite frequently on paper too. How do you construct a simple electromagnet? Then most of the time, the question is going to ask you, you can draw a diagram as part of your answer, and more often than not, they will give you full marks if you have a correctly drawn, properly labeled diagram. So the diagram is very, very simple. What do? You have a battery connected to a wire with a switch, of course, because we have to turn it on and off. And then we will have the wire being coiled into a solenoid. So this right here is a solenoid. And that solenoid is going to be wrapped around a soft iron core. When you have to describe, you describe it as solenoid is wrapped around a soft iron core and the battery provides direct current. Basically just that. You don't need to explain a magnetic field formation because this is just a describe question. They will also sometimes ask how you make the magnetic field strength of the electromagnet stronger. Well, if you don't already have a soft iron core, you add the soft iron core to increase the magnetic field strength, and then you can use a stronger current. You can increase the current by increasing the voltage of the battery. So use a higher voltage battery. And of course, you can increase the number of turns on the coil. So the number of turns on the coil will increase the magnetic field strength by increasing the magnetic field line density. And by the way, guys, always make sure that you increase the number of turns in the coil, not make more coils, but increase the number of turns of coils, okay? It's number of turns, not number of coils. Number of coils would mean individual coils, so you have one coil, two coil, whereas number of turns means the number of actual turns on the actual coil. Okay, and that's pretty much it for the electromagnet. Now we move on to the motor effect. Now, motor effect, once again, it is also a phenomenon, but of course, we will also need to know an explanation. So the motor effect for a current carrying wire. It states that a current carrying wire will always experience a magnetic force when it is placed in a magnetic field, as long as the direction of the current it is carrying is not parallel to the magnetic field. That is part of the specification, so it's good to know, but you won't really have to bother with that once until you get to like A levels and your OSSD. And motor effect also applies to any charged particle, so protons, electrons, alpha, betas. Any charged particle passing through a magnetic field will experience a magnetic force, of course, as long as its motion is not parallel to the direction of the magnetic field. So here is an example, an aluminum foil being placed in a magnetic field. If the current is switched on, it's going to go upwards like that. And here we have an electron being placed between two opposite poles of a bar magnet, and the electron curves like that because of an electromagnetic force being exerted on it. Now, we'll have to find out why that happens. So we are talking about an explanation. So why does the wire move when it is placed between two opposite poles of a magnet? Well, we're going to have a circular magnetic field around the current carrying wire. We know that from electromagnetism. And we're also going to have a magnetic field of the permanent magnet because that's just how the magnet is. What happens is that there is going to be an interaction between those two magnetic fields, which is going to lead to a stronger magnetic field at some part and a weaker magnetic field at some part. And this is going to cause a net magnetic force in a particular direction, in this case, upwards. Okay, so for the explanation, you just basically write this. It's going to give you 2 marks minimum, and the keyword here is interact. So circular magnetic field of the current carrying wire interacts with the magnetic field of the permanent magnet, which causes a force. So the force will, describing and measuring the force will give you an extra mark. So how do you determine the direction? How do you guess the direction, right? So we use the left-hand rule. This is called Fleming's left-hand motor rule. That's the full name of it. But just calling it left-hand rule is also sufficient. So left-hand rule, it is used to predict the direction of the force, the direction of the conventional current, and the direction of the magnetic field given 2 of those pieces of information. So one of them will be unknown, will be given the 2 other pieces of information, and we have to predict one of them. Okay. So how do we do it? Well, we use our left hand. So left hand, we use it, and we're going to be using 3 fingers. We're going to use the thumb, we're going to use the first finger, the index finger, and we're going to use the middle finger, the second finger. So it's also very easy to memorize because we can use the cues within the words describing the fingers. So in the thumb, right, in the thumb, we spell it using the word M. Now, M represents the motion. Motion represents the magnetic force. So it is going to be the direction in which the wire is moving or the direction in which the magnetic force is being exerted. The first finger, our index finger, it represents the field, the magnetic field direction because we spell it using an F, right? First finger. The second finger, C, represents the current, the conventional current, so positive to negative, okay? Which is why we have to be very careful when we are looking at electrons because the electron's direction is going to be opposite to the conventional current. But for most of the questions in international GCSE level, we are almost always working with conventional current or a positive particle, so it's not much to sweat about. And of course, guys, remember that the direction of the movement of the wire, the motion of the magnetic force, the direction of the conventional current, and the direction of the magnetic field are going to be at right angles to each other. They are going to be mutually perpendicular. So here is a summary of all the rules that you need to know for your electromagnetic effects. Straight wire, solenoid, right-hand grip rule, and your left-hand rule for the motor effects. Then we move on to the uses of the motor effect. This one is going to be the most important, perhaps, content of Unit 6. Okay, so when we are using the motor effect, we have 2 examples that we need to know and understand and be able to describe and explain. These are the simple DC motor and the moving coil speaker. Arguably, the simple DC motor is much more difficult to write, and also you have like 3 different question types, whereas the moving coil loudspeaker, you only have 1 question type, so you just memorize it and you just write it. It's very easy. So let's look at the simple DC motor. First of all, what does a simple DC motor do? The simple DC motor, it uses electricity to rotate, to turn, and that turning effect can be attached to different items. For example, if you want to do it in a drill, you just attach it to a something with a drill. If you wanted to put it in a motor, you put it in a motor. If you want to put it in a pump, you put it in a pump. Okay. So it uses the motor effect by using electricity to rotate continuously. And of course, the key components that help it rotate continuously are going to be the spring ring commutator and the carbon brushes. So that's the structure of a simple DC motor. You should know the structure to be able to understand how it functions. So first question that we need to know, how does the coil start to rotate? Okay, we're just talking about the start of the rotation. We don't care about how it continues to rotate. For this question, we're just talking about how it starts to rotate. So for the start of the rotation, guys, we basically write the motor effect, and then we talk about the different directions. So first of all, motor effect, right? So current flowing through the coil causes a magnetic field around it. That's electromagnetism. We know that. This magnetic field is going to interact with the magnetic field of the permanent magnet, causing a force on each side of the coil. So 1, 2, 3 is basically just writing about the motor effect. Very simple. Now, the confusing part comes to in number 4, okay? Now, because in a simple DC motor, our coil is like this, right? We're going to have the current direction opposite in each side. So if this side is positive, current is going to be going into the page on this side. But on this side, the current is going to be coming out of coming out of this page. So what happens is, to describe that, we need to say current direction is opposite in each side of the coil. Current direction is opposite in each side of the coil. So what happens is, if you try using the left-hand rule, you're going to find that the direction of the force is also going to be opposite on each side of the coil. So on this side, the force is actually going to be downwards, and on the right side, the force is actually going to be upwards. So force on each side of the coil is opposite. Now, because the force on each side of the coil is opposite, it's going to cause a rotation effect. In this case, it's going to rotate anti-clockwise. This causes the coil to rotate. So yeah, that's pretty much it for this question. How does it start to rotate? write the motor effect, and then talk about the current direction being opposite on each side, and then therefore the force direction being opposite on each side, and then you say because of that it starts to rotate. The keyword here, guys, is going to be the term rotate. Okay, it's not just moving; it's moving in such a way that it's going to be rotating about an axis. So the keyword rotate is actually going to be very important. Next question. Now this question gonna be a little bit more confusing. It's going to talk about why the motor continues to rotate. Okay. And the question can sometimes come in the form of explaining the role of the carbon brushes and the split-ring commutator, because the carbon brushes and the commutator are going to be the ones doing the heavy lifting when it comes to continuous rotation. So first of all, what does the carbon brush do? Well, the carbon brush provides the current connection to the commutator. So it's basically going to be sitting between the commutator and the coil, and the wire connecting it to the DC current supply. Now, the commutator, guys, is going to be rotating along with the coil. So on this diagram, you can see as the coil rotates, the commutator, the red part, also starts to rotate. And what it does is that once it reaches the half turn, right, the midway point, the commutator is going to reverse the direction of the current by changing the terminals to which each side of the coil is connected. So in this case, guys, initially, side A is connected to the negative terminal, side B to the positive. But as it rotates and passes through the halfway point, the side B becomes connected to the negative terminal, and side A becomes connected to the positive terminal. And therefore, side A no longer carries current out of the page, but it now carries current into the page. Now, by flipping the direction of the current, what it does is that if you use the left-hand rule, it's going to reverse the direction of the force acting on each side of the coil. So initially, as you can see, side A, right, the force is upwards. But after passing to the halfway point, side A now carries current downward. Now the force direction is now downwards. So what it does is that by flipping the direction of the force, it keeps the coil rotating in the same direction. If A continue to have force upwards, the coil will not continue to rotate clockwise. It will rotate anti-clockwise. So it will go from rotating clockwise to anti-clockwise. We do not want that. So we had to switch the current and switch the direction of the force on each side of the coil to cause the coil to continue rotating in the same direction. So we say this reverses the direction of the force on each side of the coil. This little phrase, each side of the coil, guys, very, very useful, makes it very, very succinct for your writing. And how does it do this? It does this by reversing the polarity of the magnetic field on each side of the coil. So as the direction of the current flips, the polarity is also going to flip. We know that from the right-hand grip rule, right? If the direction of the magnetic field flips, if the direction of the current flips, the direction of the magnetic field also flips, right? Now, if you need an extra mark, you can mention that, but you can also skip this if you don't want to. And because of that, the coil continues to rotate in the same direction. And of course, the little note that we have to make here is about the half turn. Now, at the half turn point, there is no force because the coil is completely and perfectly vertical. The reason it rotates just past it is because of its angular momentum, and it rotates farther because of the current swapping by the commutator. So if you didn't have the commutator, the current cannot swap. So it's just going to rotate slightly a bit. And then it's going to go back, and then it's going to stop because it's going to eventually lose its momentum and kinetic energy. So yeah, without the commutator, the coil will stop at the half turn because the current cannot be reversed. There has been a question in 2024 November about this topic, so it's also a good idea to understand what is happening at the half turn. And this is an example question from 2025 June paper 1P. This question combines both of the questions that we have talked about, okay? So it's going to ask you about why the coil starts to rotate and then why it continues to rotate. So here, as you can see, I have broken down the question into two parts. Why the coil turns breaks down into why the coil starts to turn, and then the continuously part breaks down into the why it rotates continuously part. And here, of course, I have also added the mark scheme so that you can reference and cross-check with your model answer. And I've also provided a model answer myself so that you can reference it to make your explanations very, very concise and still land the mark points that you need. And another question, guys, this is actually very, very common as well. Describe 3 ways to make the motor rotate faster. Now, this is actually like very basic motor effect, and it also references the concept of the electromagnetism. So basically what you do is you increase the magnetic field strength by increasing the number of turns in the coil. As the magnetic field strength increases, the force also increases, making the motor rotate faster. And then you increase the magnetic field strength by using the stronger magnet itself. So if the magnet is stronger, field strength is stronger, force is stronger, rotate faster. And of course, you can also increase the field strength by increasing the current, and you increase the current by increasing the voltage. So basically, it's the same as making a stronger electromagnet, but you apply it in the motor effect. So these 3 points, make sure to know. The question is gonna give you at least 1 point, and then they're gonna ask you, like, okay, what other 2 methods do we have? And you're gonna have to answer 2 of these in the answer. Right. And of course, here is an example question with an example masking. Say a modification that will increase the force on the loudspeaker coil. So how do you make a stronger motor effect? Increase the strength of the magnetic field, use a larger current, use more turns of wire on the loudspeaker coil. And then we move on to our loudspeaker. Loudspeaker, guys, is very, very easy. Just memorize this entire page and you can answer every single question because it's exactly the same thing. Okay, so first of all, the structure of a loudspeaker, we have a cylinder magnet and then we have a paper cone. A paper cone is attached to the coil. So the current is going to be carried in this coil. So what happens is that around this coil, there is going to be a magnetic field because of the current. We know that from electromagnetism. And then we have the permanent magnetic field because it's a cylinder magnet and it's going to go into here. So what happens is that the magnetic field around the coil is going to interact with the magnetic field around the permanent magnet, causing a force on the coil. So the coil will move and thereby the paper cone will also move. But what we are trying to do here is we are trying to generate sound waves, and sound waves are longitudinal waves, and we need vibrations. So what do? We need the coil to move back and forth so that it vibrates the air particles. In order to do that, we use the alternating current. Now, because we use alternating current, the current's direction is going to be continuously changing. As the direction of the current continuously changes, the polarity of the magnetic field also continuously changes. Now, here the word polarity becomes very, very useful. Okay, the polarity of the magnetic field is also going to be continuously changing. Now, we call that a changing magnetic field. So AC current generates a changing magnetic field. Because the direction of the magnetic field is continuously changing, the force on the coil is also going to continuously reverse, causing the cone to move right and left, back and forth continuously. Because it moves back and forth continuously, the cone is going to vibrate the air particles, generating a longitudinal wave, which is going to be a sound wave. And if you have a hard time memorizing this one, I also have a flow chart so that you know the exact key points and the exact things that happen, making it easier to memorize the steps. And of course, I have also attached a sample question with a sample mark scheme so that you can, you can make your model answers much better. So yeah, here is the summary for the motor effect. What is the motor effect? Explain the motor effect. How do you determine the directions using the left-hand rule? How do you make a faster motor effect? How do you make the motor rotate faster? And then, of course, the simple DC motor, we have questions. Why does a loop of wire rotate? Why does it continue to rotate? What is the role of the commutator and the copper brushes? And of course, in the moving coil speaker, how does it work? Very, very frequent question. Then, of course, we move on to, guys, electromagnetic induction. Electromagnetic induction is actually very, very easy and very, very simple. But of course, because it's very simple, we don't have as many questions as the motor effect. So electromagnetic induction is a phenomenon in which when you move a magnetic field near a current, near a conductor, voltage gets induced in the conductor and current flows in the conductor if it's in a complete circuit. So how do we write? Well, if we are moving the wire, we say the wire is moved through the magnetic field. Here, the word move is going to be very important. So make sure you say move. If something is rotating, you say it's rotating, okay? And because of this movement, it is going to cut the magnetic field lines. We do not need to know ideas about magnetic flux linkage and changing magnetic fields. That's for higher levels. So just say it cuts the magnetic field lines, and because it cuts the magnetic field line, it induces a voltage in the wire. Remember, guys, what is induced is the voltage, is not the current. Okay, don't say current is induced, say voltage is induced. And because voltage is induced, it causes a current to flow. Remember, guys, from electricity, V is equal to IR. The wire will have a resistance. We now have a voltage, so we can have a current. Voltage is induced, current is flowing. Why does the current flow? Because we have a complete circuit. And a side note and a little bit of a advanced concept that we might need, and I have seen before once, is that the voltage causes the current to flow because voltage is actually electromagnetic force. So that causes a force on the electrons, okay? So in higher levels, you will encounter that more frequently, but in iGCSE, it's quite rare. It's just a side note. And of course, if we are moving the magnet, well, the magnet will move. The magnetic field lines are cut by the wire. I use the passive voice here because the magnet itself is moving, and this causes a voltage induction, and therefore the current will flow. And of course, guys, remember the direction of the current depends on the direction of the movement. So for example, if we were moving the magnet in this direction, and then we pull it out, right? The direction of the voltage, and therefore the current is going to change. So as you can see in this diagram, if we move it to the right, the voltage direction is actually to the right. But if we pull it out to the left, the direction of the voltage is going to be to the negative side. So we have some questions with ammeters, that ask you to explain why the ammeter behaves in such a way. So please make sure you know about the idea of direction and how the movement direction impacts the current direction. And of course, as usual, just like we did in the motor effect, how do we increase the voltage? Well, we increase the voltage. The key concept here is that you want to increase the number of magnetic field lines that are being cut per second and thereby increase the voltage. So if you want to increase the number of magnetic field lines, what you do is you increase the number of turns of wire on the coil. Like if you have more turns on the wire, the number of magnetic field lines that can be cut increases because you have more surface area, right? So you increase the number of turns. You can also use a stronger magnet because if you use a stronger magnet, the magnetic field density, the magnetic field strength is going to be higher, and therefore the magnetic field line density is higher. So because you have more magnetic field lines, more of them can get cut by the wire, therefore causing a higher voltage. And of course, you can also move the wire or the magnet faster because per second, right, the number of magnetic field lines are going to get cut are going to increase if you're moving the wire much faster. So those three points also very important. And of course, guys, last but not least, we have the transformer and large scale transmission of electricity. Remember, guys, this is gonna be a paper 2 topic, so you do not need to revise this for your paper 1 topic coming next week. So first of all, we need to know about the large scale transmission of electricity and the role transformers play in them. This diagram you should be able to draw, not the entire diagram, but this part where the transformers are and the pylons themselves. So when we are transmitting electricity on a large scale, what happens is that the power station, right, produces high current electricity. And when we have a high current, the problem is that it's going to cause a heating effect. We knew that from unit 2, right? It's going to cause a heating effect. And when it causes a heating effect, some of the energy is going to be transferred into the thermal store of the wires, and that means that the electrical transfer, the useful electrical transfer is going to reduce. So we're not going to have as efficient of an electrical transfer of energy. So in order to fix this problem, we put in a step-up transformer. A step-up transformer up here refers to an increase in voltage, right? What it does is it increases the voltage. This in turn decreases the current because we have the equation P is equal to VI, right? And the power is constant because the power station can only generate a certain amount of energy per second, right? So power is constant. So we have is that VI is equal to VI. So if we increase the voltage, the current is going to decrease because power is constant. And what happens is that because we have a lower current through the cables, the energy loss is going to be much lower because we have a reduced heating effect. And therefore, it allows us to transfer electrical energy more efficiently. And remember, guys, in a step-up transformer, the number of turns on the secondary coil is going to be much higher than the number of turns on the primary coil, thereby causing an increase in the voltage and a decrease in the current. Now, a step-down transformer does the opposite thing. It steps down the voltage. It decreases the voltage. And because it decreases the voltage, the current is going to increase. The reason the voltage must decrease is because we need it for safety reasons and to reduce the risk of electrocution. The voltage that we are going to be carrying here are going to be in thousands of voltage, and we do not want that for our residential commercial use. We want only in hundreds levels, so 110 volts, something like that for European countries, and 230 volts, something like that for America and Asian countries. Yeah, so we reduce the voltage to reduce the risk of electrocution for safety reasons. So you need to be able to explain why these roles are important. And of course, this slide is basically explaining why step-up transformers and step-down transformers are important. In the next slide, we're going to look at how they work. And of course, some notation here, NP, NS, IP, IS, basically just talking about the number of turns and the current in the primary and the secondary coil. Primary coil, remember guys, is the coil on the left and the secondary coil is the coil on the right. Here is another way of writing down why they are important. So step-up transformer, increase the voltage, decrease the current. Now, how do they do that? They do that by having more turns on the secondary coil. They reduce the heating effect of the current, and therefore they reduce their energy waste in the form of thermal energy. Step-down transformer, they do the opposite. They decrease the voltage, increase the current. They decrease the voltage for safety reasons, prevent the electrocution of people using the electricity. This is because the number of turns on the primary coil is higher than the number of turns on the secondary coil. Now, how does that voltage change happen? Explain the operation of a step-up/step-down transformer. Well, we're going to do a lot of electromagnetic induction principles in this transformer. So first of all, one current passes through the primary coil, magnetic field is produced. Again, it is going to be electromagnetism. There is going to be a magnetic field around here. But because we are using AC current, the current around is going to be continuously changing. Okay, and that creates a changing magnetic field. Now, a changing magnetic field is going to be passing through the soft iron core as well, and the iron core strengthens the magnetic field. That is the only reason why the magnetic field here can ever reach the secondary coil in the first place. So what happens is that the magnetic field of the primary coil is going to be cutting the secondary coil. So the secondary coil cuts the changing magnetic field. Now, because the magnetic field is always changing, it is going to get continuously cut by the secondary coil. And this cutting, as per the principles of EM induction, is going to induce a voltage in the secondary coil. And because the secondary coil is a complete circuit, it is going to induce current. And because we use AC here, the current here is also going to become AC. In a step-up transformer, because the number of turns on the secondary coil is greater, it's going to increase the voltage. In the primary coil, because the number of turns on the primary coil is greater, it's going to decrease the voltage. Okay, so if you're asking about step-up transformer, write this. If the question is asking about step-up transformer, write this part. So these 5 plus this or this. And of course, make sure you know how to draw the diagrams. It's very, very easy. Just draw a picture frame, 2 rectangles, and draw, these coils. The only thing that's important is to make sure that you have this correct number of turns, relatively speaking. So if it's step up, more on the secondary. If it's step down, more on the primary. And this question, guys, is quite annoying of a question, but we have to understand this. Okay, why don't transformers work with direct current? Well, transformers don't work with direct current because they need a changing magnetic field in order to cut the secondary coil. If we are using a DC source, right, what happens is that we have a magnetic field, but that magnetic field is a constant magnetic field. It's not changing. And because it's not changing, it's only going to cut the secondary coil like once when you turn it on. And that's not going to work, okay? And because it's not going to cut the secondary coil continuously, we're not going to have induction of voltage. So if you want to write this for exam purposes, you say, for induction, a changing magnetic field is required. But because the current is not changing direction in the DC source, only a constant magnetic field can be generated. And because there's no cutting of magnetic field lines, no voltage will be induced in the secondary coil, and thereby, transformers cannot work with DC sources. And then we come to calculations. Like calculations are going to be important as well. And of course, remember guys, this is going to be in paper 2. So first calculation, guys, is going to be the formula of turns ratio being equal to voltage ratio. So the number of turns on the primary coil over the number of turns on the secondary coil is going to be equal to the voltage in the primary coil over the voltage in the secondary coil. Remember guys, if you are looking for secondary, you can put secondary upwards, but of course, make sure you put secondary on both sides. So if it's secondary coil, for the number of turns, you put secondary coil here and voltage on the secondary coil here as well. Make sure you flip both sides, okay? And now we have power in is equal to power out, assuming that the transformer is 100% efficient equation. So I primary is times voltage primary is equal to I secondary times voltage secondary. Sometimes we will also write I in V in, and I out V out. Both works. Just make sure you get your calculations correct. Alright guys, that's pretty much it for Unit 6. And I have also put together some useful video resources where you can make sure you visualize things like the transformer and the loudspeaker and the electromotor, because sometimes if you don't understand it, you have to visualize it to really see how it's going on. So if your exam is in, let's say, 26 October and you still have time, make sure you watch these videos to visually understand it. And of course, I also have the links to some simulations so that you can mess around with the settings and see how things change when you change the factors. Alright, I think that's pretty much it for Unit 6. Have a blast with your revision, and I'll see you guys in Unit 7. Unit 7, let's get to nuclear physics. We have to talk about nuclear decay, ionizing radiation, radioactivity, measuring radioactivity, half-life, and of course, fission and fusion, and how we utilize nuclear energy. So let's start off with the basics. This is a nucleus. The plural form would be nuclei, and we represent nuclei using this symbol. So this little number at the bottom represents the proton number or the atomic number, and the larger number at the top represents the nuclear number, which is the sum of the protons and the neutrons. X would represent the chemical symbol of that element. So if it's barium, it would be Ba. If it's helium, it would be He, and so on. And then we talk about isotopes. You need to know this definition. Isotopes are nuclei of the same element with the same number of protons but a different number of neutrons. That will get you 2 marks. So an example here would be hydrogen with no neutrons, 1 neutron, and 2 neutron. Please remember this, these 2 isotopes, because it will become useful when we talk about fusion. Then we talk about radioactive decay or nuclear decay. Now, isotopes, some of them are stable. They like being in that form. Some of them, however, are unstable. They do not enjoy being in that form, and so they want to change. So how did they change? Well, they change by nuclear decay, radioactive decay. These unstable isotopes become stable by emitting nuclear radiation, and that process is called nuclear decay. And remember guys, nuclear decay is a random process, okay? This word is going to get you a mark in some questions. Nuclear decay happens randomly, and so we cannot predict it. An example here would be the decay of uranium-238 into thorium-234, releasing alpha-2He4 as nuclear radiation. The parent nucleus is unstable, but the daughter nucleus would be stable. Sometimes the daughter nucleus would also be unstable, and the daughter nucleus itself can undergo further nuclear decay, and that will lead to the formation of nuclear decay chains, but that is not necessary to know at international GCSE level. Next up, we need to know how to balance nuclear equations. This is actually very, very important, and you will get 3 marks for these questions. So basically, all you have to do is make sure that the nucleon number and the proton number are conserved, meaning that the nucleon number on the left is equal to the sum of the nucleon number on the right, and the proton number on the left is equal to the sum of the proton numbers on the right. So when you have negative numbers like -1, make sure you work it out separately for each side. So for example, on the right side will have 7 plus -1, which on the left side would be equal to 6. Then we have measuring radioactivity and what radioactivity is. Now, radioactivity is the rate at which nuclear decay happens. It is given as counts per second, where one count is equal to one nuclear decay. One nucleus turns into a stable nucleus per second. And one count per second is equal to 1 becquerel. This is the SI unit, 1 BQ. If you want to write it in long form, you write BAC/QUEREL with a small p. Now, radioactivity can be measured using a GM Geiger-Müller tube and a counter. Remember, you need a counter to be able to measure the count rate. Without a counter, GM tube can only detect the presence of radiation. Radioactivity can also be called count rate, and this right here is a diagram looking at the GM tube and the counter. And another thing that can detect radiation is photographic film. Remember guys, photographic film can detect radiation, but it cannot measure or count the radioactivity. And then we have to talk about half-life, guys. What is half-life? Well, half-life is the average time taken for the number of radioactive nuclei to decrease by half, or the average time taken for the radioactivity to decrease by half. That definition is gonna give you 2 marks, and you must know this. And of course, in the place of number of radioactive nuclei, you can also write amount of the unstable isotope, amount of the radioactive isotope, or the mass of the radioactive isotope. Now, the thing that we need to know is that when the nuclear decay happens, the number of parent nuclei are going to decrease. And as the number of parent nuclei, the unstable isotopes, decrease, the radioactivity is also going to decrease with it. So what happens is that after a certain period of time, the amount is going to decrease by half. And the average time taken for that to happen, we call that the half-life. Now, half-life is going to be on average the same. So every time one half-life passes, the initial mass or the initial number of nuclei or the initial radioactivity is going to decrease by half. So you need to understand the concept. The concept of half-life is going to be very, very important even when we look at uses of radioactivity. Because we're gonna have to look at how half-life impacts, how we use radioactive materials. Then, of course, we have our calculation things. First of all, how do we find the half-life of a material on a graph? Remember, guys, whenever we talk about half-life, okay, we need to remember that half-life is time taken. Okay, half-life is time taken. So we're gonna have to look at the x-axis where the time will be given. So how do we do this? We start by finding the initial mass or the radioactivity or the number of radioactive nuclei. So usually what we do is we look at the very, very start at 0 and we look at the initial count rate or the initial radioactivity or the number of nuclei. And then we find the half of that. So in this example, the initial would be 58 count per second. So we half that, we get 29. So what we're going to do next is that we're going to find the time taken for the radioactivity to reach 29 counts per second. So we identify 29 first, and then we look at the x-axis to find the time taken to reach that radioactivity value, and we find that it is going to be 68 seconds. So the half-life is going to be 68 seconds. Now, that is how you do your calculation. And another thing that we need to know here is, if we take a look at this graph, we see that not all the points lie on the graph. So some of the points are above the line, some of the points are below the line. And the question is going to ask you, okay, explain why many of the points do not lie on the curve. And the way you answer is to say, because radioactive decay is a random process, and so there is no fixed rate of decay. Sometimes it might decay much more quickly, and therefore the count rate decreases much more faster. Sometimes it decays much more slowly than you expect, so it's going to be the count rate is going to be slightly higher than expected. This line is just the average estimate. It is the best fit line. Okay, so make sure you understand and know that as well. Next up, we have calculation of the number of nuclei remaining after a radioactive decay. So if you are going to do this step by step, this is how you do it. So first of all, you need to find how many half-lives has passed. So you're going to do the time taken, right? They're going to give you the time taken, the time period. So for example, it's like 1,000 years, 2,000 years. They're going to give you the time taken, and you divide that by the half-life. So if half-life is 500 years, you divide 1,000 years divided by the 500 years. So that will be 2 half-lives. And what we do is we're going to multiply the starting number of nuclei with 1/2 for the number of times which we get from here. So if it was 2 half-lives, we're going to half it twice. If it was 3 half-lives, we're going to half it 3 times, okay? So an example of that question is right here. A sample of pure thorium-239 contains 4 times number of 14 atoms. The half-life of thorium is 7,300 years. After 2000 and after 22,000 years, how many thorium-239 atoms remain in this sample? So we're gonna first calculate the number of half-lives that pass. So we take 22,000, divide by 7,300, which gives us 3 half-lives. So 3 half-lives has passed. So after 1 half-life, 4 times 10 to the power 14 is gonna half into 2 times 10 to the power 14. After 2 half-life, it's gonna half into 1 times 10 to the power 14, and after 3 half-life, it's gonna half into 5 times 10 to the power 13. So the number of parent nuclear remaining will be 5 times 10 to the power 13 nuclear. And of course, if you want to find the number of total nuclei that has been produced, you can also do that by subtracting the number of parent nuclei remaining from the initial. So initially we have 4 times 10 to the power 14, but now we only have 5 times 10 to the power 13 remaining. So what happened to the rest? Well, the rest become the total nuclei. So the total nuclei would be 3.5 times 10 to the power 14 nuclei. And you can also do this with a formula, but the formula is actually quite, has lots of terms. And in Edexcel International GCSE, the questions for calculations are going to be at least 3 marks. And the reason they gave you 3 marks is because they want to see your steps. If you use the formula, you can't see the steps anymore, so I don't really recommend using the formula. The reason I'm mentioning the formula and how you can use it is because you can double check and verify that your step-by-step calculation is correct. So once you have done the step-by-step working out, you can recheck your answer by plugging the values into this equation. So the number of nuclei remaining after a period of t is going to be equal to the starting amount times half to the power t over t half, where t half is the half-life and t is the time period that they give it. So going back to the question on here, the initial amount is 4 times 10 to the power 14, multiplying 1 over 2, the whole to the power. Time taken is 22,000 over 7,300, which is the half-life, which will give us 5 times 10 to the power 13, and therefore we can cross-check and make sure that our answer is correct. So please do not use the formula for your actual calculations. Use it for double-checking. And of course, if you don't want to memorize it, don't memorize it. It will be fine. Just make sure that you get these steps correct and you will be on your way to bank full marks for these questions. Then we have to talk about background radiation. Background radiation is very, very important. This is quite a common definition. So what is background radiation? Background radiation is low-level ionizing radiation that is always present everywhere, but we do not have a single obvious source to identify for it because it's coming from multiple sources within the environment. For example, it's coming from cosmic rays in the atmosphere, it's coming from radon gas down below, and it's also coming from the remnants of medical equipment and military activity such as nuclear bomb testing. So when you're going to write the definition, I recommend writing these 2 plus 1 example. The marking scheme does change a little bit from year to year, so make sure you bank all these points in order to ensure your safety of your marks. Then we move on to discussing ionizing radiation. And guys, this is perhaps the most important concept that you need to know in Unit 7. Yes, we do have fission and fusion, but that's, a separate topic. This right here is going to be the gold mine. This right here is going to be the essence, okay? Because we're going to get lots of questions regarding the applications of radioactivity. When we do our applications, we don't need to memorize the exact uses, the exact use cases, the name of the use cases. We're going to get questions in more often than not, novel contexts. And the way we solve those questions is by looking at the properties of ionizing radiation and how the properties of different types of ionizing radiation reflect the use cases in those applications. And of course, we also need to know the concept of half-life to be able to answer those questions. So let's take a look. So ionizing radiation is nuclear radiation that can cause ionization. And what is ionization? You need to know this. Ionization is the removal of an electron from an atom to form an ion. So when ionizing radiation comes in, it's going to knock an electron off of its orbit in the atom, and therefore it's going to lose an electron, and therefore it's going to have a charge, and that charged particle, therefore we call it an ion. So what kind of ionizing radiation do we need to know? We need to know about alpha, beta, and gamma in great detail, and we need to know a little bit about neutron radiation. Remember guys, neutron radiation is not primary ionization, it is going to be secondary ionization, indirect ionization. Okay, starting with alpha particles. Now, alpha particles, by the way, guys, when we are looking at alpha, beta, and gamma, the things that we need to know are going to be the nature of the particle, the ionizing ability, the penetration power, and the effect it has on the parent nucleus when that particular particle or nuclear radiation is produced. So when we look at alpha particles, we're going to look at particles that are fast and energetic, and the nature of the alpha particle is that it is a helium nucleus that contains 2 protons and 2 neutrons. So the only difference between a normal helium nucleus in the air and a helium nucleus that is considered an alpha particle is that an alpha particle is super fast. It is approximately 10% of the speed of light. So we're looking at something like 3 times 10 power 7 meters per second. And the ionizing ability of alpha particles are very high. They are able to remove an electron very easily from an atom. And the reason is because they have a very high mass and a very high charge. And so they can easily knock electrons off of atoms. Their penetration power, however, is very low. They can easily be stopped by paper or a few centimeters of air. And that is because they have a high mass and a high charge. And so when they bump into atoms, it is very easy to stop them. And the effect on the parent nucleus is that whenever particles are produced, the nuclear number is going to decrease by 4. The proton number or the atomic number is going to decrease by 2 because we have 2 fewer neutrons and 2 fewer protons in the parent nucleus. So the daughter nucleus will have 2 fewer neutrons and 2 fewer protons compared to the parent nucleus. Next up, beta particles. Beta particles are going to be actually quite a little bit difficult to remember in terms of how they form because it's quite weird, but stick with me and you'll be fine. So first of all, what is its nature? The nature of a beta particle is that it is a fast energetic electron. And remember guys, the beta particle that we need to know at iGCSE level is a beta minus particle, okay? They are also beta positive beta plus particles, but we do not need to know them for iGCSE level. So only beta minus particle. So beta minus particle is a fast energetic electron. It goes as fast as 0.9 C, so 2.7 times 10 power 8 meters per second. And it has a very high ionizing ability, but compared to the alpha, it is going to be less. But compared to gamma, it is going to be more ionizing. And the penetration power is also going to be moderate. It is going to be more penetrating than alpha, but not as much as gamma. So both of these you can say is going to be moderate. And if you want to stop beta particles, you need to use a few centimeters of aluminium. So how do beta particles form? Well, let's take a look at this diagram from Save My Exams. Okay, so in a nucleus, we're going to have a neutron. A neutron is neutral, so it has no charge. What happens is that the neutron is going to break apart into a beta particle, a proton, and something called an anti-electron neutrino. You do not need to know this particle for your iGCSE exams. You just need to remember these two to be able to remember how it forms. So basically, a neutron has 0 charge. Electron has -1 charge, a proton has a +1 charge. So when you add a -1 and a +1 together, you get 0. So the charges balance out. So basically, a neutron converts into an electron and a proton, and the charges add together again. So the effect on the parent nucleus is that it's going to have 1 fewer neutron, but 1 more proton. So basically, the nucleon number is going to remain unchanged because the sum of the neutron and the protons will remain the same. However, the proton number is going to increase by 1 because you now have an additional proton. And of course, an example would be the classic 6014 to 714. 7 and 14. So this is carbon 14 getting converted into 7 and 14, hydrogen 14, and producing a beta minus particle. And as you can see, we have 1 more proton in the nucleus because of how a neutron converts into a proton and an electron. Lastly, we have gamma radiation. Gamma radiation is actually very simple. It is just a high energy electromagnetic radiation. It is the highest frequency portion of the EM spectrum. It travels at the speed of light, of course, because it is an EM wave, and the ionizing ability of it is the lowest because waves do not have charge and they do not have mass, so they find it quite difficult for them to knock electrons off of atoms. Penetration power, however, is the highest because it is very difficult to stop them. They are simply waves, so they can pass through materials very easily. If you want to stop them, it requires a thick block of lead or concrete in order to stop them. Now, how does gamma radiation form? We'll take a look at this diagram. Gamma radiation forms when you have a nucleus with a high energy, and we refer to those nuclei as excited nuclei. Now, excited nuclei are described using an asterisk next on the top right of the chemical symbol, or you can also write an M next to the nucleon number. So what happens is that the excited state, it has so much energy, so it's going to release the extra energy. So when it converts from an excited state to a stable, a ground or relaxed state, it's going to release the extra energy as the gamma ray. So it's going to go from an excited state unstable to a relaxed state stable by releasing energy as gamma rays. And of course, because gamma rays have no mass and no charge, there is going to be no effect on the nucleon number, no effect on the proton number. It's just going to be 0, gamma 0. An example of this is technetium-99m converting into basic technetium-99. Remember, guys, M refers to excited state of an isotope. And of course, this is going to be useful in medicine, and you can see some questions regarding technetium-99m in your past papers as well. Okay, then we look at penetration power. So penetration power is going to be the greatest for gamma, is going to be the least for alpha, and beta is going to be in between. And we need to remember which materials can stop alpha, beta, and gamma, okay? And the way I like to remember this is using the mnemonic PAL, PAL. So alpha, beta, gamma, PAL. P represents paper, so alpha can be stopped by paper or a few centimeters of air. Beta can be stopped by aluminium, and gamma can be stopped by lead or concrete. So you need to remember those materials in order to investigate the different penetration powers. We're going to see that becoming useful in a few seconds. And here is the summary of all the ionizing radiations. We have alpha, beta, and gamma. Now the thing that we have not yet talked about is neutron radiation. Now neutron radiation, you don't need to know about the penetration power and ionizing ability. You only need to know the effect of neutron radiation on the parent nucleus because that is part of the specification. However, I have not seen a single question regarding neutron radiation in the past few papers, so who knows, it might come up in the near future. So neutron radiation is basically just a high energy neutron. It is produced when nuclei have way too many neutrons. So basically they have one extra neutron that they need to get rid of so that the nucleus becomes stable. So what impact does it have? Well, because we're going to lose one neutron from the nucleus, what's going to happen is that the nucleon number is going to decrease by 1. However, the proton number remains the same because the protons are not going to change. So the effect of the nucleus of a neutron radiation is that the nucleon number is going to decrease by 1, and it happens because the nucleus has an excess of neutrons. Then comes the big one. Now, this one is going to be one of the biggest topics in Unit 7 because you can get asked regarding how you will set up the exact experiment, and you can also get asked explanation questions regarding this. You're going to have to analyze the data, and you're going to have to explain what type of radiation is being produced by the source depending on the results that you get. So first of all, let's look at the experimental setup, okay? So the things that we're going to need are going to be a GM2 and encounter, of course, to measure the Count rate and our radioactive source. And we will also need some kind of absorber material to be able to determine which type of radiation is being produced because alpha, beta, and gamma can be stopped by different types of absorber materials. So let's look at the startup, guys. First of all, you use your GM2 plus counter to find the mean background radiation count. So how do you find the mean background radiation count? Well, you make sure that your radioactive source is removed or it is kept in a lead-lined box so that the radiation of the actual radioactive source does not contribute to the measurement of background radiations. So first of all, we find the mean background radiation rate. Of course, we have to do this several times and find the mean. Then we place the radioactive source and find the total count rate. So when the radiation from the radioactive source comes out, we're going to get the radiation of that radioactive source plus the radiation from the background radiation. So if you want to find the actual count rate caused by the radioactive source, we find the difference between the total count rate and the background count rate. Now, this process from 1 to 3 is called correcting for background count rate, and sometimes the question might ask you separately, okay, describe how the student can do the setup and correct for background count. So when they ask you like that, you can answer from 1 to 3. And of course, for our complete analysis of whether the source is producing alpha, beta, or gamma, we'll have to take these steps. So we're going to have to repeat several times and find the mean of the real count rate. And then we have to repeat the entire process by placing paper, aluminium, and lead. And we're going to have to look at how the count rate changes when we place paper, when we place aluminium, and when we place lead. Now, we're then going to compare the count rate and analyze and evaluate the data. So if when we place the paper, the count rate reduces significantly, we can conclude that the radioactive source is a big alpha emitter. If nothing happens with paper, we can conclude that it's not producing any of the particles. If the current reduces significantly when we place aluminium, we can conclude that it is a beta emitter. However, if nothing happens with aluminium, then we're going to have to look at lead. When we place lead and the current significantly reduces, then we can conclude that it is going to be a gamma emitter. We also need to know some control variables. The control variables are the distance between the GM tube and the radioactive source. Of course, if you change the distance, the current rate will alter quite a bit, so you do not want that. And you also want to measure the current rate for the same time. So if you're going to measure for 1 minute, measure for 1 minute for all radioactive sources. And of course, the mass of the radioactive source, if possible, should be the same. And we also have some safety precautions for this experiment, which I will be discussing later when we talk about how we reduce the risk of irradiation. So here is a summary, guys. Alpha, beta, and gamma. Alpha is P, beta is aluminum, gamma is lead. And of course, guys, remember the mnemonic PAL. Okay, alpha, beta, gamma, PAL. And here are some example questions and what you should write for those example questions. And of course, this file will be in the description, so you can go and check this out. Next up is going to be a topic from Unit 6. This actually belongs to Unit 6, but I like to put this in Unit 7 because we learn about charged particles, alpha, beta, and gamma in Unit 7. And the thing is that these questions mostly pop up on paper 2 as well. Okay, so you're going to see this a lot on paper 2. So we're going to talk about the effect of magnetic fields on charged particles. Now, we already know from Unit 6, right, the Morter effect, that when charged particles pass through magnetic fields, there is going to be a magnetic force on them as long as their motion is not parallel to the direction of the magnetic field. So it's basically the same principle here, and we still use the left-hand rule. Okay, so just to revise the left-hand rule real quick, you use your left hand, your thumb represents the motion or the magnetic force, your first finger represents the direction of the magnetic field, and your second finger represents the direction of the currents. When we're looking at charged particles, we're actually talking about the motion of positively charged particles. So if we are looking at negatively charged particles, we're going to have to take the opposite direction of it. Okay, so if the electron is going this way, our second finger will actually have to point that way. Okay, and here are some examples of the particles have been following a curved path because of it traveling into an magnetic field. And one thing that we need to know here is that when the magnetic field strength increases, the magnetic force is going to become greater. And of course, because we know that F is equal to ma, and when F increases, the acceleration is also going to increase. Now, when the acceleration increases, guys, the speed of the particle may or may not increase. However, the velocity of the particle will increase. And because we know that the velocity is the rate of change of displacement, right, the direction of the velocity is going to be changing much more quickly. And so if we have a stronger magnetic field, what happens is that the particle is going to be following a tighter curve. Okay, and so the circular motion is going to be following a shorter radius. So do have that in mind. This is going to be drawing the ideas from Unit 1 as well, not just Unit 6. So when you have questions like these, specifically on paper 2, make sure you understand the concept of acceleration and how that is going to affect the path of the proton or the particle. And of course, here are some examples with diagrams from Save My Exams with both positive and negative particles. Do remember, guys, these examples are taken from IB Physics, so you do not actually need to know every single thing for your iGCSEs, but yeah, just make sure that you prepare a little bit and you're familiar with this. And here's an example question from 2024 June paper 2 PR and an example flowchart explaining how things work here. Then we move on to the applications of radioactivity and the dangers of radioactivity, as well as how to protect people from experiencing those dangers. So applications of radioactivity, you can basically split that into medicine and industry. In past papers, there are more questions on medicine, and medicine breaks down into diagnostics, treatment, and sterilization. Industry breaks down into different uses such as smoke detectors, radiography, gauging, thickness control, and radiocarbon dating. So let's start with sterilization of medical equipment by irradiation. Now, sterilization can also be done on food and beverages, and if you are a human bio student, you will of course know that sterilization is a big part of food preservation, right, using gamma radiation. Now, here's an example scenario to look at, okay? So basically, we are using gamma radiation to kill the bacteria in this apple. Now, is this apple safe to eat? Yes, it is. Why? Well, first of all, the gamma rays have killed the microbes and the bacteria, so you do not have any microorganisms to cause any gastrointestinal issues. Secondly, the apple is not radioactive because it does not come into contact with the radioactive source itself. So that is perhaps one of the most common conceptions regarding why people do not want to eat radioactively sterilized food is because they have the misconception that the food itself become radioactive, but the food itself does not become radioactive. Now, to describe the scenario, we have actually two words. Okay, we say that the apple has been irradiated, not contaminated, and that leads us to our next very important subtopic: irradiation and contamination. Irradiation is simply the exposure to ionizing radiation, so alpha particles, beta particles, gamma radiation, and neutron radiation. You get hit by that, you are irradiated. Okay, no, there is no contact with the radioactive source, there is no transfer of radioactive material, and the object therefore does not become radioactive because the object does not contain radioactive isotopes whatsoever. An example of that is when you sterilize medical equipment or food using irradiation. Contamination, however, is the transfer of radioactive material to a non-radioactive object because it becomes in contact with the radioactive source. So for example, if you have, let's say, uranium-238 and you touch uranium-238, now you're going to have uranium-238 atoms and isotopes on your skin. So your skin becomes radioactive because uranium-238 is actively decaying on your body. Okay, so that's the difference between irradiation and contamination. Make sure you are able to write the difference and describe what irradiation and contamination means. This is actually very, very important. Anyways, back to our uses. Going back to medicine, we first look at diagnostics. Now, diagnostics is looking at what is wrong in our body. There are two types of diagnostic uses for radioactive particles. We have, first of all, tracing. Now, tracing is when you put a radioactive isotope into your body and you find out where it goes. So is it accumulating in some places or is it distributed throughout the body? Okay, and we're of course going to be using a radioactive isotope. So an example use is going to be the use of iodine 131. Iodine 131, guys, is radioactive. I think it is a beta emitter, and basically what happens is that the thyroid, right, we have the thyroid in the neck. Thyroid needs iodine to produce its hormones. So when you have iodine in your blood, that iodine is going to get taken up by your thyroid. So once it gets taken up by your thyroid and it gets it gets integrated into your thyroid tissue, the iodine 131 is going to emit its radiation. And what we do is we use a specialized camera to detect the radiation coming from iodine 131. And by you doing that, what we can do is we can observe the shape of the thyroid, okay? And we can look for abnormal enlargements, tumors, any kind of masses, and see if we have any thyroid abnormalities. And one thing that we need to know here, okay, is the concept of what kind of radioisotope to use. You don't need to remember exactly how iodine 131 works. You need to remember and you need to be able to understand, okay, the choice of radioisotope when it comes to a particular use, in this case, tracing. So when we are doing tracing, the ideal radioisotope should, number one, have a short half-life. And that is because we want it to decay quickly. If it decays quickly, it's going to remain in the body only for a short while. And that is thereby going to reduce the radiation exposure time for healthy body tissue. If it remains in the body for too long, it's going to cause prolonged radiation exposure, which we do not want. Second, we want to use a radioisotope that is either a beta or a gamma emitter. Why? Because beta and gamma have a high penetration power, higher than alpha. And so these guys can pass through the body tissue and reach the specialized cameras. And they also have, compared to alpha, a lower ionizing ability, which is going to reduce its capacity to do any kind of damage to healthy body tissue. So that is very important to understand. Okay, if we understand that, we're going to be able to answer most of these questions. So the property of beta and gamma and alpha, and why we use a short half-life for our tracing uses. Secondly, we have imaging. Imaging is basically using radiation to form visuals of particular structures, for example, brain, to see if there are any cerebral abnormalities. And then we have treatment. Now, treatment is basically using gamma radiation to kill particular cells. So an example that I would like to talk about is gamma radio knife surgery. I don't know if it's gamma radio knife surgery or gamma knife radio surgery, but whatever, the concept is actually quite interesting, and it might come up in your exams. So basically what we do with gamma radio knife surgery is we have a tumor in the brain and we want to get rid of that tumor. But the problem with gamma rays is that they are not that ionizing. So a single gamma ray is not sufficient to kill a tumor. So what we do is we line up multiple gamma rays and we make sure that the point at which they converge is directly on the target, the tumor. So when multiple gamma rays converge at that point, it's going to lead to an increased ionizing ability, which will therefore kill the tumor or the cancer cells. In other parts, however, because they are not converging, the individual gamma rays themselves are not sufficiently ionizing enough to cause damage to healthy brain tissue. So that's actually a very, very smart use of gamma radiation. And you might be asked that in your exam. I don't know, probably, maybe not. But yeah, it's a good thinking exercise to understand how gamma rays function. Next up, industry. Now, industry, guys, I don't think there are many questions of radioactive uses in industry. The only thing that I've seen is like a small detector. So just sit back, relax, and listen to this. Think of this as a textbook reading revision. So first of all, gamma radiography, basically you look at the inside of objects, forming a visual picture. Same as photography, but you use gamma instead of photons, instead of light. Then we have gauging. Now, gauging is when you use radioactive materials to find how much of a material is there inside like an irregularly shaped object. So if there are too many objects, the radiation count will decrease, and you can therefore translate that into too many items in the container. If the radiation count is high, then you can translate that into there are not a lot of items in the container. So that's what gauging is basically. And then we have using radioactive tracers to detect for leakages in pipes. This one is actually very, very interesting, okay? So what we do, okay, is we're going to look at pipes that are underground. And if we want to investigate for leakages, if they're actually like very, very deep underground, it's actually very hard to visually inspect them. So what we do is we put a gamma source into the pipe. And the gamma source is going to emit gamma radiation upwards. And we're going to use a detector, for example, a GM tube encounter, to measure the radioactivity coming from the gamma source. So if there are no leaks, the gamma source should be emitting the gamma radiation at a normal rate. However, if there is a leak, what's going to happen is that the water is going to leak from the pipe and is going to accumulate in that area. So the gamma sources, along with the water, is going to accumulate in that area. So in that part, the count rate coming from the gamma radiation is going to be significantly much higher. So if our detector finds that the count rate is significantly much higher in that area, then we can conclude that it is going to be a leakage. On the other hand, we can't use alpha and beta particles. Why? Because they are not penetrating enough. Remember, guys, alpha can be stopped by a few centimeters of air and beta can be stopped by aluminium. So if you are deep underground, beta is not coming up. Next up, we need to take a look at thickness control. Now, thickness control is also quite interesting. So basically what we do with thickness control is we need to make sure that the thickness of the material is exactly the way we want. So what we do is we have a feedback loop, okay? We're going to have a gamma source and a detector. Gamma is going to come across like this. And the detector is going to measure how much gamma is coming through that material. If too much gamma is coming through, then this material is too thin, and that's going to give feedback to the rollers. The rollers are going to move apart and make it a little bit thicker. If too little gamma is coming through to the detector, then we know that the metal sheet is going to be too thick. Rollers are going to compress together and make the material thinner. And that's going to happen until we get the exact amount of thickness, which is going to be measured by a very fixed and exact range of gamma radiation coming through to the detector. So here are some diagrams to help you visualize the uses. And then we move on to radiocarbon dating. Now, the concept of radiocarbon dating is that it appeared on 2020 November. So what we do is basically we have a living sample and a non-living sample. And what we're going to do is we're going to find out when that dead sample died. So for example, a tree, right? So basically what we do is that in a living sample, the amount of carbon-14 should remain constant. And that's because, for example, right, a tree would be taking in carbon dioxide, and it would also be giving out carbon dioxide, and it will also be losing C14 because of its natural decay. So because the input and output are going to be balanced, the amount of C14 in a normal living tree should be constant. So it will be at 100%. However, if the tree has died, it can no longer absorb C14 from the atmosphere. And what that translates to is that the C14 will just decay by itself and it's going to eventually decrease. And that is shown by this graph. And as time passes, the amount of C14 is going to decrease in the dead sample. So what we do is we're going to measure, okay, the activity of a living sample. So for a living sample, the percentage or the activity should be 100%. But for a dead sample, it would be less than 100%. So we measure the activity of C14 from a dead sample, and then we're going to look at this graph and see, okay, our dead sample has only 50% activity or 50% remaining. So what does 50% mean? After how much time should only 50% remain? So what we do is we look at the graph and we say, oh, after one half-life, there should be 50%. And therefore, that means that our dead sample passed away one half-life ago, which will be 5,700 years ago. So that's how we do radiocarbon dating. Now, the question that came up in 2020 November was that because of nuclear testing, right, the amount of carbon-14 in the trees actually increased beyond their natural rate of consumption. So when they died, instead of having only 50%, they're going to have something like 60%. And the question asks, how does this affect the age of the trees? Well, just look at the graph. It's very simple. If you have 60% when you should be having 50%, the graph, the x-axis, right, the point on the x-axis is going to shift to the left. And therefore, the number of half-lives that's passed is actually lower than normal. And therefore, the trees are going to appear younger than they should. So nuclear weapon testing can therefore interfere with radiocarbon dating. And another thing is that radiocarbon dating cannot be used for samples that are older than 55,000 years, because after like 57,000 years or 10 half-lives, the amount of carbon-14 remaining is like 0.1%, and so if you detect the activity, it's just pretty much not noticeable at all. And then, of course, dangers of ionizing radiation. Ionizing radiation damages DNA, which causes mutation, which leads to cancer. So how do we minimize risk of irradiation? This is also going to be quite useful for your investigation question. They might ask that, okay, we're doing that investigation where we measure the count rate. What kind of safety precautions do we take, as students and teachers? Well, first of all, you want to make sure that you are handling the radioactive sources using tongs, and you are handling them at arm's length. So as far as this, okay? You do not want to place them close to your body. You want to make sure that when you are handling radioactive sources, it's as far away from you as possible. And you want to make sure that you are not pointing the source towards anyone. Okay, make sure you keep the radioactive source as far away from everyone as possible. And when that radioactive material is not in use, it should be stored in lead-lined boxes. Remember, lead is a very, very good absorber of gamma. And of course, if we use concrete, it's even better because it can absorb neutrons. So make sure you store them in lead-lined boxes. If you're going to be working with something more serious, for example, a gamma source, you can also wear lead aprons. Now, these are what lead aprons look like. And of course, make sure you wear your gloves. And another thing is you want to make sure you minimize your time handling radioactive substances. So when you put them out of the box, you make sure that you use them as effectively as possible, and then as soon as you're done with that, put them back into your lead boxes. This is also important for doctors, specifically radiologists who work with X-ray. So if you work with X-ray, what you would do is you would stand in another room, not in the same room as the patient receiving the X-ray, and you want to make sure that you are not exposed to radiation, to X-rays and radiation on a daily basis. So make sure you stand in another room and minimize time in which you are exposed to the radiation. And of course, the boxes in which those things are kept should be clearly labeled as radioactive, and make sure you use only small amounts. And if you want to throw away them, make sure you throw away them underwater, and of course, send them to specialized radioactive waste facilities. And then we talk about how we dispose of radioactive material. This is actually a question that came up, I think, on 2021, and we have not seen other questions like this, so we just memorized the mark scheme. So what do we do? First of all, we dilute the material in seawater. When we dilute it, it's less concentrated, so less radioactive. And of course, we have to store them in a site with high security. Of course, we do not want people stealing radioactive materials and using them for bad purposes. So put them in a place with a specialized facility. And the specialized facility should have protection against natural disasters, for example, earthquakes. Because if the building gets destroyed, the radioactive material is going to go everywhere. It's going to go into the ground, it's going to go into the groundwater, it's going to pollute groundwater sources. We do not want such kind of contamination. And we need to use machines when we are removing them. Okay, we do not want to be doing, handling them with our hands. We want to be using specialized machines. And of course, we can store them underwater down below, keep them away from people. And of course, we want to store them in strong containers that can resist corrosion, that can prevent irradiation. So materials such as concrete will do. So yeah, this is gonna be a memorization question. Haven't seen this come up in a while, but just to be prepared, make sure you memorize that. And of course, this is just an alternative question, same concepts here as well. This is the example mark scheme from that particular question. Okay, so last part of Unit 7, guys, we have nuclear energy. So nuclear energy can be harnessed in two methods, fission and fusion. Now, what is fission? Well, fission is when a large nucleus splits apart into smaller delta nuclei and neutrons. So, fusion, however, is the opposite. It is when smaller nuclei, so at least two nuclei, join together to form a larger nucleus. Okay, so make sure you are able to define fission and fusion to be able to tell the difference between those two. What happens in both processes, however, is that in both processes, mass is lost and energy is released. So this is basically mass energy conversion. You're going to have to learn this in your grade 12 physics. But for now, basically just know that whenever fission or fusion happens, you lose mass and then mass gets converted into a lot of energy because we have E is equal to delta mc squared. You do not need to know this in the exam. You do not need to calculate in this exam either. So first of all, let's take a look at nuclear fission. Okay, the example that we need to know by heart, the example that we need to know really, really well is the nuclear fission of uranium-235. Now, how do we describe the nuclear fission of uranium-235? Well, we start with the initial nucleus. So initially, we have one nucleus, right? That uranium-235 nucleus is going to absorb a neutron. So it absorbs a neutron, and when it absorbs a neutron, it forms uranium-236. Now, uranium-236 it is going to be unstable. Sorry. Because it has one extra neutron. So because it absorbs one extra neutron, it is unstable and is going to break apart into two delta nuclei. Barium-144 and kryptonium, I think it's krypton 89. So you don't need to know the exact names of the delta nuclei. Just know that it splits apart into delta nuclei and it releases at least two or more neutrons. Okay, so in this case, it releases 3 neutrons. So because it releases neutrons, these neutrons released by the initial nucleus are going to be absorbed by other uranium-235 nuclei, and so those other uranium-235 nuclei also split apart, and those also release neutrons, and they also split apart, release neutrons, split apart, and therefore it leads to a domino effect. We call the domino effect a chain reaction, and that chain reaction is utilized in nuclear power stations. So make sure you know how to describe the fission of uranium-235 really, really well. It's quite a common question. Now let's take a look at nuclear reactors, guys. So for nuclear reactors, you don't need to know how it really works, but for Unit 4 purposes, I'm going to tell you a little bit about it. So basically, we have this nuclear reactor. This is where the fission is going to be happening. And what happens is that when the fission happens, energy is transferred from the nuclear store of the uranium to the thermal store of the water because we have the waters going around here, right? And when the water gains thermal energy, it's going to become steam. When it becomes steam, it's going to move through the turbines, and that turbine is going to turn the generator, and that generator is going to cause electrical working, which will generate our electricity. Okay, so this is for Unit 4 purposes. For Unit 7, the thing that we need to know here is how the different components of the nuclear reactor work. So first of all, we have the main guy, which is going to be our fuel rods. Now, what do fuel rods do? They provide the fissile material. Now, fissile material basically means material that undergoes fission. So you can say it provides fissile material, or specifically you can say it provides uranium-235. Then we have the graphite moderator. Now what graphite moderator do is that it slows down the neutrons for efficient fusion, for efficient fission. Now fission will not really happen if we have too fast of neutrons because the uranium-235 nuclei cannot absorb them. So if you want efficient fission, we want to make sure that the neutrons are slow and those neutrons can be absorbed by the uranium-235. And then we have our radiation shielding. Now, radiation shielding is made of concrete. So you can also see it being described as a concrete or steel wall. So what that shielding does is that the shielding absorbs neutrons to prevent irradiation of workers. So if the question basically says it is going to be a concrete layer, you can also use the word shielding. It acts as a shielding, gets you 1 mark. And then talk about how the shielding works. It absorbs the neutrons to prevent irradiation of the worker, gets you 2 marks. Okay, very nice. And then we have control rods. Now, control rods are going to be the ones controlling the rate at which the fission reaction is happening. What it does is that the control rods absorb the neutrons and they control how fast fission happens. So when the control morphs are moved inside the reactor, they can absorb more neutrons. The reaction rate slows down. If they move out, fewer neutrons are absorbed. Fission happens much faster. So moving the control rods up and down inside the reactor is going to be how we are controlling the response to demand. So if we have a high electricity demand, we move the control rods out, faster fission, more electricity. So something like that. Okay, and here is an example showing how the control rods work. So this is an example question as well. Why is it dangerous to remove most of the control rods? So if we remove most of the control rods, fewer neutrons will be absorbed, so fission rate is going to increase. So we're going to have a lot of energy. And if we have too much energy, right, the reactor is going to get super, super hot. So if we get super, super hot, it can lead to an increase in pressure, which can lead to explosions, which can lead to the reactor melting down. Okay. And this is gonna be, of course, for unit 4 purposes as well. Discuss the advantage and disadvantage of generating electricity in nuclear power plants. So in nuclear power plants, guys, advantages are there are no CO2, and of course, the fuel will last a long time because you only need a small amount to generate energy. So only a small amount of uranium, and of course, because of that, we have a high energy density. However, the disadvantages is that the radioactive waste is going to be produced. So the barium that we talked about, the krypton that we talked about, they are also radioactive. They are not stable themselves, so they can lead to decay chains. So what we have to do is we will have to store them in specialized facilities, which is going to be not easy. And of course, it is non-renewable. So even if we have a lot of them, and even if we only need a little bit of them, we will have to one day we will have to switch to another energy source because we will run out of them. And of course, there are high risks of accidents and it's very dangerous. For example, the Fukushima accident in Japan led to a very devastating state in 2011. So because the Fukushima power plant actually stopped working, what happens is that the energy supply to Tokyo reduced drastically. So as you can see in this picture, Tokyo was not as bright as it will usually be because of the Fukushima power plant actually shutting down because of the accident. And of course, that means that we have lots of consequences. It's not just about the accident itself being radioactive, but when we lose an actual power plant, a city can go without normal electricity supply for days, even months, so which is not economically favorable as well. And then of course we have nuclear fusion. Nuclear fusion, I remember, it's when smaller nuclei get together to form a larger nucleus. The process in which masses law and energy is released. So if you are asked to define nuclear fusion for 3 marks, this is what you would write. And of course, guys, we need to know that nuclear fusion happens in the core of stars, okay? Students often skip this part because they just think it's an example, but no, it's not an example. It is required in the specification. You need to know that nuclear fusion happens in the core of the stars. For example, in the sun, we have 1s2 plus 1s3 becoming 2h3, 4 plus 0, and 1. And of course, this is happening in the main sequence stage. And of course, we're going to take a deeper look at that when we look at astrophysics. And the thing with fusion is we actually require 2 conditions. We need very, very, very high temperature. We're talking about millions of degrees Celsius, and we need high pressure. We're talking about, I think, millions of pascals as well. So why do we need those conditions? Let's take a look, guys. When we are doing fusion, we basically have 2 nuclei. And we know that nuclei are positively charged. So nuclei, do they want to get close to each other? Of course not. They hate each other. Why? Because they are both positively charged, and same charges, they repel each other. So if we want them to get close together, we need to push them together. So for that, we need a high temperature and high pressure. So first of all, when I'm going to answer these kind of questions, what I need to do is I need to identify the problem first. So the problem is that the nuclei repel each other because they are positively charged. So that's the problem. And the problem, we need to solve that using these conditions. So how do these conditions solve the problem? Well, high temperature provide the nuclei with a high kinetic energy. So the nuclei can move faster. Now, when the nuclei move faster, they can overcome the force of repulsion between the nuclei much more easily, and therefore they are more likely to get close enough for fusion. The thing with pressure is that when you have high pressure, it's going to force the nuclei closer to each other, and when the nuclei are closer to each other, there's going to be a higher chance of them getting close to fusing. So those are the 2 conditions, and you must be able to explain why those 2 conditions are needed. And of course, when you apply the reverse condition, they were also gonna ask, okay, why does nuclear fusion does not work at low temperature and low pressure? Basically, just reverse this and answer. And here are some advantages and disadvantages of generating electricity using fusion reactors. So basically, the question is going to ask you about the safety advantages of fusion reactors. So fusion reactors, why are they good? Of course, no CO2, very efficient, lots of energy produced. And of course, we use hydrogen gas, so 1H2, 1H2 plus 1H3. Hydrogen is very abundant, so very, very easy to generate energy using that. And it has lots of safety advantages. For example, no radioactive waste. The only thing that we have is helium that gets produced. And some neutrons, and of course there are no long-term storage problem because we do not have these radioactive waste coming out, and we do not have risk of meltdown because it's controlled, and there is less risk of cancer because less risk of irradiation of worker. We only have neutron radiation, which can easily stop by concrete, and of course we do not need shielding because even the neutrons are not going to be that dangerous, and the reactants are less hazardous because we only use hydrogen. The disadvantage, of course, is that temperature and pressure condition. It's not easy to get those millions of degrees Celsius, and of course it's still non-renewable at the end of the day. So yeah, here are the discussion of the safety advantages of a fusion reactor. And yeah, that's pretty much it for Unit 7, guys. That's pretty much it for Unit 7. Um, yeah, so Unit 7, basically, not a lot of calculation. The only calculation that you have to do is for your nuclear half-life decay thingies. So lots of theory, but make sure, like I said before, make sure you get your alpha, beta, gamma properties right. Make sure you get your half-life concept right. Most students still struggle with half-life because they do not understand the concept that half-life is the time taken for the radioactivity to decrease by half. Okay, make sure that you have the concept really, really grounded, and of course, make sure you need to memorize. You need to memorize just the fission and fusion, the conditions, and etc. and etc. Okay, so yeah, that's pretty much it for Unit 7. Have a blast with your revision, and I'll see you guys in Unit 8. Bye bye. All right, Unit 8, the last one. Let's go, guys. Here's a toast for you for making it this far. So let's get it. Astrophysics, space physics. What do we have under space physics? We have motion in the universe, looking at galaxies, universe, galaxies, solar systems, and of course planets, moons, and satellites. Stellar evolution, how stars change and evolve over time, and of course our big paper two topic, the study of the universe, cosmology. Let's dive into it. First and foremost, our first chapter, motion in the universe. Now, this page covers the entire chapter. So first of all, some astronomical terms to know. Universe. Universe is a collection of billions of stars. Galaxy collection of billions of, oh sorry, I think I made a mistake here. Ooh, the universe is a large collection of billions of galaxies. There you go. Galaxies. The universe is a collection of billions of galaxies, and a galaxy is a large collection of billions of stars. And of course, the galaxy in which we live is the Milky Way galaxy. Then we have gravitational force and gravitational field strength. Now, gravitational field strength is basically how much force is exerted on a mass that exists within the gravitational field of a big mass. So, for example, if you have a planet and something enters that planet's gravitational field, how much of a pull would that object field? So gravitational field strength varies from star to star, planet to planet. So it depends on the mass of the planet or the star, as well as the radius of the planet or the star. Remember, guys, it is going to be an inverse square law, just like in Coulomb's law in electrostatics. So as the distance increases, the radius, the gravitational field strength is going to decrease, dramatically. And of course, as the mass increases, the gravitational field strength is going to increase. So larger stars and larger planets will have a higher gravitational field strength. And the equation is Fg is equal to Gm1 m2 over r squared. This is the gravitational force, and the gravitational field strength is gm1 over r squared. You do not need to know this for your international GCSE levels. This is just an extension. And then the equation that we actually need to know is the orbital speed. So assuming that the orbit is a perfect circle, which it is not, we just assumed it. We say v is equal to 2 pi r over t. That's because the distance that we travel is a circumference, which is 2 pi r, and the time period, and the time taken is the time period of the star. So v is equal to 2 pi r over capital T. And then we look at the astronomical objects, how stars, planets, and moons and comets orbit. So star is at the center of a solar system. In our case, it's the sun. And planets orbit the star. And moons natural satellites orbit the planet, and there will also be artificial satellites orbiting the planet. And the comet will also orbit the star, but the comet will have a more elliptical shape. So the star is not at the center of its orbit is going to be more to the edge of its orbit. So to compare, okay, the different properties of planets, moons, and comets' orbits, we can use this table. So a planet orbits a star, a comet also orbits a star, so that's a similarity. But the moon or the artificial satellite orbits the planet. For both planets and moons, the object of orbit is at the center because their orbits are more circular. However, for a comet, the star is not at the center of an orbit. And also, for a comet, the speed of the orbit is going to change depending on how close it is to the star. So when the comet gets close to the star, it is going to be moving much faster. But when it gets farther from the star, it is going to move more slowly because the gravitational field strength and the gravitational force is going to be much stronger when it is closer to the star. Whereas for the stars, whereas for the planets and the satellites, they are going to have a constant orbital speed because the distance between them and the planet does not change that much. And of course, because of the circular nature of their orbits, they are going to have a shorter orbital path, but comets will have a longer orbital path because of their more elliptical nature of the orbit. And orbit of the comets can have multiple planes, so they can be like this. Okay, that can be the orbit of a comet, but whereas the orbit of a planet and a moon, they are only in one plane, so something like this. So that's pretty much it for motion of the universe. Then we go to stellar evolution. First of all, we take a look at the property of the temperature and the surface color. So the thing that we need to know is that the surface color of a star is related to its surface temperature. So the redder the star, the cooler it is. Okay, so it's counterintuitive. Usually we would think, okay, red flames are bright, right? Are hot, right? But actually, blue flames are much hotter. So the bluer the planet, the bluer the star, the hotter it is. So we actually go red, orange, yellow, white, and then blue. Of course, it's gonna be ROY, and then you put white in between, and then you put blue. Of course, you can't go from blue to white. You can only go from white to blue. So red, orange, yellow, white, and blue. It gets increasingly hotter. And you can also use the mnemonic BWYOR, but Y you already do represents blue, white, yellow, orange, red. So this is just a neat mnemonic. And then comes the big boy, stellar evolution. So stellar evolution, the pathway depends on what mass of star you are talking about. The path is going to change depending on the mass of the star. So if the mass of the star is approximately the same as the solar mass, it's going to be a straightforward linear evolution. However, if it's going to be significantly greater than the mass of the sun, it is going to take two different paths. Okay, so let's take a look at the details. Before we go into the details, let's take a look at the stages first. So for the star, which is approximately the same as the sun, it's going to follow this path. So all stars, they began as stellar nebula, and then it becomes a protostar, and then it becomes a main sequence star. One thing to note is that a star is not really a star until it becomes a main sequence star. Protostars are not stars, they are more like neo-stars, okay? They're just beginning, not really a star yet. And that's because for a star to become a star, there has to be nuclear fusion happening in it. Once the main sequence stage expires, it's going to expand into a red giant and then become a white dwarf with the planetary nebula surrounding it. And of course, eventually the white dwarf may become a black dwarf, but because our universe is quite young, there have not been black dwarfs in the history of the universe. If the star is much more massive than a sun, it's going to follow a different route. So stellar nebula, protostar, main sequence, same path. But instead of being a normal red giant, it is going to become a red supergiant, so massive, huge. And it's going to explode in an event known as a supernova, and the remnant of the supernova could either be a neutron star or a black hole. So once you know these stages, which one comes after which, you are quite set. You are quite good. However, there are explanation questions, okay, asking you to detail what happens when the star goes from which to which. So that's what I'm going to teach you now, okay? So the key factors that you need to have in mind are going to be the interaction of forces, the occurrence of nuclear fusion, and how that impacts the temperature and pressure in a star. So the concept that you need to know is about the balance of two forces. Now, you do not need to be naming these two forces except for the gravitational force at international GCSE level, but I believe that understanding how these two forces work will help you really, really, memorize it much more easily, because once you know how these forces are working, memorizing the steps actually becomes a lot easier. So first of all, what are the forces that we need to know? The forces are going to be gravitational force and the outward radiation pressure. So outward radiation pressure is the pressure that comes from nuclear fusion, because nuclear fusion generates thermal energy, and that thermal energy is going to cause the gases inside the star to expand, and that's going to cause the star to expand outwards. So our radiation pressure, it depends on how much fusion is happening. And remember, fusion depends on the temperature and pressure, like we just discussed previously in Unit 7. So if we don't have a good enough pressure, there's no fusion, and our radiation pressure is not going to be good. If there is a lot of pressure and temperature, there's going to be a lot of fusion, and there's going to be a lot of our radiation pressure. So what happens is that if the gravitational force is greater than the our radiation pressure, the star is going to contract. If the inverse is true, it's going to expand. Okay, so that's the concept that we need to know when we are talking about stars changing stages. So let's take a look at the mass, at the common pathway, right? Whether it's a star with the same mass as the sun or much higher than the sun, this is going to be the common pathway that we're following. So all stars start with a nebula. Remember, guys, nebula is a cloud of gas and dust particles, okay? And the cloud of gas and dust particles, they're going to pull each other closer together because of the gravitational force. At this instant, our radiation pressure is zero because there's no fusion. And because of the gravitational force pulling the particles together, eventually those particles are going to collapse into a solid of a protostar. Remember, protostar is not yet a star. Now, what happens when there's gonna be a collapsing into a protostar is that the temperature and the pressure are going to increase, because instead of being a huge cloud, it is now this tight, dense, solid mass. So the temperature and the pressure are going to increase because of that collapse. Now, as the temperature and pressure continue to increase as the protostar continues to collapse, what's going to happen is that we're going to reach that 100 million degrees Celsius threshold, allowing hydrogen fusion to begin. So once hydrogen fusion begins, we get a star, and that star is called a main sequence star. Now, because we have hydrogen fusion, that is generating the energy, which is causing gases to expand, which is causing the planet to expand outwards, we have our outward radiation pressure. But because we also have the masses, we're still going to have the gravitational contraction. So the gravitational contraction and the outward radiation pressure are going to be balanced. And because of that, in a main sequence star, there are no changes in size. It's just going to be stable hydrogen fusion balanced by the gravitational force. And currently, our sun is in that state, which is why nothing is happening and we are able to live because of the light energy it provides. So what happens, okay, when a star starts to go past main sequence? Well, there is actually an intermediate step between the main sequence and the red giant. So what has to happen is that, okay, one day, the fusion of hydrogen will stop because, hydrogen will kind of run out, but we can't really say hydrogen runs out because hydrogen is kind of infinite. But for some reason, hydrogen fusion will stop. So when that stops, okay, the gravitational force is going to become significantly much greater than our outward radiation pressure. So therefore, our star is going to contract. When our star contracts, the temperature and pressure are going to significantly increase. And this is going to re-trigger our hydrogen fusion, which is going to flip the tables and cause the outward radiation pressure to become significantly greater than our gravitational force. And therefore, we now have more outward radiation pressure than inward gravitational force, causing the star to expand. Now, if the star has a mass approximately equal to the solar mass, it is going to expand into a red giant. Now, the star has expanded. And of course, because the star has expanded, right, it is going to have a lower temperature than the main sequence. And that is indicated by, of course, a red color. In the main sequence, it's going to be yellow, but here it's going to be red. Why? Because it's going to be cooler than a main sequence. Of course, once it expands, it's going to become stable for a while, and then we're going to have helium fusion starting when it becomes stable. So helium fusion, helium is going to be heavier than hydrogen, so we're going to have helium fusing into things like carbon and nitrogen, right? And again, for some reason, helium is going to stop fusing as well. And when helium stops fusing, same thing happens. Gravitational force overcomes the outward radiation pressure, which is going to cause the star to collapse very, very quickly. Now, when the star collapses, what happens is that the core, okay, the core means the center part of the red giant, yeah, is going to collapse into a white, super dense solid called a white dwarf. Whereas the outer part of the star, so the outer part of the star is going to be ejected and released as a planetary nebula. And of course, because we are looking at a star that has a color that is white, we can see that the color of the white dwarf, the temperature of the white dwarf is going to be much higher than both main sequence and the red supergiant. And that's pretty much it for the star whose mass is approximately the same as the solar mass. And of course, in the future, they could become black dwarf, but our universe is still young. And of course, generally, the bigger the star, the better it is. So if we compare main sequence, red giant, and white dwarf, we could say that the red giant is going to be the brightest, main sequence the second, and our white dwarf the least brightest. So here's a summary I wrote in prose form. The star starts as a nebula, cloud of dust and gas. They pull together by gravitational force, collapsing into a protostar. Because of that, the pressure and temperature continue to increase, and when the pressure and temperature are good enough, hydrogen fusion will start. Therefore, it becomes a main sequence. Now, when the hydrogen fusion stops, the star is going to contract and expand rapidly again because hydrogen fusion gets activated again and becomes a red giant, and the red giant helium fusion will go on. And when the helium fusion stops, the core is going to collapse into white dwarf, whereas the outer part of the star is going to release as a planetary nebula. And of course, when we're talking about brightness and temperature, like I said before, brightness and temperature are going to increase in the protostar stage, and then red giant is going to be much cooler. And of course, white dwarf is going to be much hotter, but main sequence and red giant are going to be much brighter. We will look at this in more detail, and you will understand this in more detail when we look at the HR diagrams. Okay, now we look at the path of the super massive stars. Okay, for the super massive stars, they're going to become a red supergiant instead of a red giant. And of course, it's the same path, right? Helium fusion happens in the red supergiant because it's causing the heavier elements to form. And the thing that happens here is that in a red supergiant, right? Because of the accumulation of heavier elements, and of course, because eventually helium fusion stops, the gravitational force is going to extremely overwhelm the outward radiation pressure. So when the gravitational force is much higher, what's going to happen is that the core of the star is going to contract rapidly and cause an implosion. Now that event is all known as a supernova. The star explodes because the gravitational force overwhelms the outward radiation pressure. Now because of that, the temperature and pressure inside are going to increase rapidly, and of course the outward radiation pressure is going to increase again, and that's going to cause the explosion on the outside, which is going to complete the supernova. So the supernova is an explosion, it's an event, and the remnant of the supernova is going to be either a neutron star or a black hole. And this depends on the initial mass. If it's super massive, it's going to become a black hole. Not super massive, then it's going to become a neutron star. And of course, neutron star is going to be super bright. Black hole is so dense that even light cannot escape its density. Even light and photons cannot escape the gravitational field generated by a black hole. So same thing here, summary, all the way to the main sequence is the same, and then we talk about how hydrogen fusion stops, star contrast, expand rapidly, become a red giant, and the temperature of the red giant is lower, and then the red giant fusion starts, and then helium fusion stops, explodes as a supernova, and leaving behind either a neutron star or a black hole, depending on its initial mass. And by the way, this should be red supergiant. By the way, I forgot to put red supergiant here. Okay, yeah, that's pretty much it for stellar evolution. And of course, I revisit to the specification to know how much we should know. Understand how stars can be classified according to their color. Know that the star's color is related to a sunrise temperature. So this is talking about like the KMA classifications. This is talking about how star color relates to temperature. And of course, this is talking about the main things that we need to know. And of course, we need to be able to describe the evolution. And by the way, guys, remember that specification demand is described, okay? So the explanation questions, yes, they used to exist, but beyond 2024, I have not seen like explanation questions, mostly just listing down the stages. So do not stress yourself out over learning the explanations. I just stated them because it's much easier to remember the stages when you understand what is actually happening. Don't stress yourself out over memorizing the explanations. Focus on getting the stages right first, okay? And the names, of course. Okay, then we get to our paper 2 topics. We will have our brightness measurements and our Hasbron-Russell diagrams. So first of all, how do we measure the brightness of a star? We measure the brightness of a star by referring to absolute magnitude. Define absolute magnitude. It is a measure of the brightness of a star at a standard distance, which is, I think, is going to be 10 parsecs or 26.3 light years, something like that. Not knowing the exact value is fine. So the thing with absolute value is that absolute value is actually negative. right? So the brighter the star, the smaller the value of the absolute magnitude. So it's going to be more negative. And of course, absolute magnitude is not affected by the distance of the star from Earth, which is why it's going to be used as the gold standard for measuring the brightness. Other methods that you can use are going to be luminosity, and luminosity is going to be the rate at which energy is emitted from the surface of a star. And the other method is going to be apparent magnitude. Now, apparent magnitude is basically saying, oh, when I look up there from the Earth, it's this bright. And of course, apparent magnitude depends on the distance, so it's not the gold standard, it's not valid. And I think I wrote them down above in the introduction part. Yeah, brightness, apparent brightness, luminosity, and absolute magnitude. So you can visit those terms in the first slide of the notes. Okay, then going back to our paper 2 content. So we talked about absolute magnitude already. We now have to talk about HR diagram. So HR diagrams are diagrams that allow you to predict the type of star by knowing the brightness and color of the star. So on the y-axis, we have absolute magnitude. Another thing that we could have is luminosity. And like I said before, absolute magnitude, the brighter it is, the more negative it is, okay? And now we have our color of the stars on the x-axis. It could also be the temperature in Kelvin. And the things that you need to know are your white dwarfs, your red giants, and your main sequence stars, and how you would draw those positions. So, how do we draw the white dwarfs? The white dwarf is going to be the easiest one. So, white dwarfs, you draw them at the position where you have white. That's very easy. You have position where we have white. And we know that white dwarfs are dwarfs, right? So, dwarfs means they are small. So, we put them in a place where the brightness is low because, like I said before, generally speaking, the brighter the star, the smaller the star, the less bright it is. The bigger the star, the brighter it is. So white dwarfs are small, so they are not that bright. So we put them in a low brightness position, and we put them in the place that aligns with white. Then we have red giants. Now red giants are big, giant. So we put them in a bright place. And of course, because they are red, we put them aligning with the red position. Those are easy. Now, the thing that's going to be quite difficult to grasp is the main sequence. So the main sequence group is actually a belt shape. Okay, so which is why we call it a main sequence belt. So when we draw the main sequence belt, what we're going to have to do is we're going to go from the top left to the bottom right. And in the middle, there's going to have to be a quite a horizontal, clear, flat region. So it's going to go from top left, going to go quite flat in the middle, and then go down to the bottom right. So it's basically like an S, right? Think of an S, and then make it like this, a sigmoid curve. And then you basically put the sigmoid curve like this. Yeah, something like that, right? So clear flatter region in the middle, going from top left to the bottom right. That's how you draw a main sequence. So the reason we do that is because there are like different variants of main sequence, right? Not all main sequence stars are yellow. Some can be, white, some can be red, depending on how hot of a star it is. So which is why we have to draw a belt. And the question types are draw the y dwarf, red giant, and main sequence, label the y and x-axis. So when you are labeling the y-axis, make sure you are labeling negative on the top, okay? Negative on the top. Negative means bright. And make sure you label your x-axis, also in terms of color or temperature. And of course, you want to guess the type of star given its position. So they might say like, oh, the star is right here, right? The star is right here. What kind of star is it? It's a main sequence. What kind of star is it? It's a red giant. What kind of star is it? It's a white dwarf. Something like that. Yeah, that's pretty much it for our stellar evolution chapter. Now we end with the biggest chapter of all time, the study of the universe, cosmology. So I made a video on cosmology a long time ago. I made a video on it uh, a long time ago. It was like 25 minutes. Really dove deep into how we memorize and how we understand it. So this is just a refresh. If you want to really understand it, go watch that video. I highly recommend that. So first of all, cosmological redshift, and we have cosmic microwave radiation. So basically what we're doing is we're proving how these two pieces of evidence support the Big Bang theory of the universe. So first of all, cosmological redshift. Cosmological redshift, how do we prove it? Well, we say that the light from distant galaxies show redshift. So basically light from distant galaxies, when they arrive to Earth, their wavelength is in the red portion of the visible spectrum. So another thing that we observe is that the galaxies that are farther from Earth, they show greater redshift. So the wavelength is going to be much longer, which means, and the thing that we know is that the greater the redshift, the faster the galaxy is moving. Why? Because we have the equation V over C is equal to delta lambda over lambda naught. Constant. So V is very proportional to delta lambda. If this is greater, this is going to be greater. So the greater the redshift, the faster the galaxy is moving. So we link this together. Okay, farther and greater redshift means that farther must mean faster. So farther away galaxies are moving faster from each other. And because the guys that are farther away are moving faster, the distance between the farther one and the less farther one are getting farther, 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 and farther. So the galaxies are moving away from each other, and therefore the universe must be expanding. And now we have cosmic microwave radiation. CMBR, how do we prove that it is actually a remnant of the Big Bang? Well, we can detect it in everywhere. Everywhere it's coming from there. Every single direction. It's not from a single source. It's kind of similar to background radiation, which we discussed in Unit 7. It's detected in every single direction, so it's not coming from a particular source. Therefore, it proves that it's coming from the Big Bang, right? And we also know that initially started as a gamma ray, but now the wavelength has increased because of the expansion of the universe. So it's now a microwave. So it now has a longer wavelength. And the increased wavelength means that the universe has cooled down because there is less energy. And therefore, we can deduce that the universe must have been much hotter in the past. And therefore, the universe must have started from a single hot and dense point in the past. So what does Redshift prove? It proves that the universe is expanding. What does CMBR prove? CMBR proves that we started from a single super dense and super hot point. Okay, so they prove the same theory, but different aspects of the same theory, which is the Big Bang theory. And of course, here's an example question. You can do more of these in my video on cosmology. But yeah, that's pretty much it for Unit 8, guys. Wow, we're done. We're done with the entirety of International GCSE Physics. That was super fast. I have never talked this fast in my entire life. But yeah, and I know, and by the way, I'm filming this on the 29th of May. And I believe that you guys have exams on the 2nd of June. So I'm gonna work super hard to get this video uploaded as fast as possible. So you guys have tonight, we have 30th and 31st and the first as well. So you guys have at least 4 days to watch this videos and revise. So yeah. I've been working super hard, guys. Even though I'm not, super free, I've been working super hard on this video. So I hope you found this video helpful. Yeah. Apart from that, good luck on your exams, and of course, a few things that I want to remind you guys to do. Okay, is that I think I'm gonna stop my screen share. Yeah, there you go. Big view of me. I think you can see me now. A few things that I want to remind you guys to do is to make sure you bring your protractors. Okay, make sure you bring your protractors. Make sure you have your calculators ready. Make sure it's in degree mode, and of course, make sure your calculators have good enough battery. And once you walk into the exam room, make sure you walk in with confidence, with calm, not panicking. And of course, once you see the question paper, do not think about anything except for the fact that you need to answer every single thing that you need to know, okay? And very important, calculations, do not mess up your calculations, okay? Calculations are going to be very important. From what I've heard from my students, this year's examination has been quite different style compared to what we used to see. So it is highly feasible that physics will also be of that nature. Okay, it's gonna be quite weird. It's gonna be quite different, right? But do not forget, you're here to answer what you know. You're here to prove that you have learned the material, that you've revised the material, okay? So what you're gonna do is the only thing that should be on your mind is I'm going to prove to the examiner as much as I know. So even if you face questions that you have never seen before, even if you face questions in novel contexts, make sure you remain calm and try to think about what you already know and how you can use that to prove that you are able to answer the question as much as you can. Alright, guys, that's pretty much it. SI units. Okay, by the way, SI units, take care of them. And of course, POT, power of 10 errors. Don't forget of them. Okay, that's pretty much it. I hope you enjoyed the video. It was super fast, but I hope it helps. So yeah, we have 4 days until physics paper 1. So yeah, see you guys in the next video. Do your best. And by the way, thank you for the support on all my videos. That's pretty much it. I'm hungry. Gonna go have lunch. Thank you once again. Bye bye. Good luck.